Look up tonight. If you find yourself beneath a clear sky, far from the glow of city lights, you might catch a glimpse of the Milky Way stretching overhead like a pale river of ancient light. It appears serene, doesn't it? A soft band of luminescence painted across the heavens. Perhaps you'll spot a shooting star, that brief flicker of brightness we often associate with wishes and wonder. The universe, at first glance, seems almost peaceful, silent, eternal in its stillness. But here's the thing about the cosmos that most people never truly grasp. It is anything but peaceful. That silence is an illusion created by distance. That stillness is a trick of timescales so vast that human perception cannot register the violence unfolding before our eyes. In truth, the universe is a realm of unimaginable catastrophe, where stars explode with the fury of 1 trillion nuclear bombs, where entire galaxies collide and tear each other apart over millions of years, where black holes devour suns and stretch them into spiraling streams of superheated matter. What appears calm from our little blue world is, in reality, a cosmic theater of destruction operating on scales that defy comprehension. And perhaps the most astonishing revelation of all is this: that violence, that destruction, that chaos, it's the reason you exist. It's the reason any of us exist. Every atom in your body, with the exception of hydrogen, was forged in the heart of a dying star or created in the cataclysmic collision of stellar corpses. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it was manufactured through cosmic catastrophes that occurred billions of years before our solar system was even born. The astronomer Carl Sagan captured this truth beautifully when he wrote that the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, and the carbon in our apple pies were all made in the interiors of collapsing stars. We are, quite literally, made of star stuff. That poetic phrase has become almost commonplace, but pause for a moment and truly consider what it means. It means that you are the ash of ancient stellar explosions. It means that the atoms comprising your heart once burned at temperatures of tens of millions of degrees inside a cosmic furnace that ultimately tore itself apart. It means that your very existence is a consequence of unimaginable violence. This is the paradox we will explore together in this journey through the mysteries behind cosmic catastrophes. The universe creates through destruction. It builds through annihilation. The same forces that would vaporize our planet in an instant if they occurred too close are the very forces that made our planet possible in the first place. There is a dark poetry to this cosmic cycle, a strange and terrible beauty to the way the universe renews itself through cataclysm. Let's begin by understanding just how vast this theater of destruction truly is. The observable universe, the portion of the cosmos from which light has had time to reach us since the Big Bang approximately 13.8 billion years ago, stretches across some 93 billion light-years in diameter. Within this inconceivable volume, astronomers estimate there exists somewhere between 200 billion and 2 trillion galaxies. That number comes from studies led by Christopher Consolis at the University of Nottingham, whose team analyzed deep space images from the Hubble Space Telescope and extrapolated to account for galaxies too faint and distant to observe directly. 2 trillion galaxies, each one containing billions upon billions of stars. The Milky Way alone, our own rather average spiral galaxy, harbors between 100 billion and 500 billion stars. Multiply that across 2 trillion galaxies, and you arrive at estimates suggesting the observable universe contains somewhere around 1 septillion stars. That's a 1 followed by 24 zeros. To put that into perspective, there are more stars in the observable universe than there are grains of sand on every beach on Earth. More stars than seconds that have elapsed since the Big Bang. More stars than human minds can meaningfully comprehend. And every single one of those stars will die. Some will fade quietly, like our own sun will in roughly 5 billion years, swelling into a red giant that will likely engulf Mercury and Venus before shedding its outer layers and collapsing into a dense white dwarf. Others will not go so gently. The most massive stars, those with 8 times the mass of our Sun or more, are destined for far more spectacular endings. They will explode as supernovae, releasing more energy in a few seconds than our Sun will emit across its entire 10 billion-year lifetime. In those brief moments of stellar death, they will outshine entire galaxies. And supernovae are not rare events. Observations of similar galaxies suggest that the Milky Way should experience a supernova roughly once every 40 to 50 years. Research conducted using the European Space Agency's integral satellite, which measured gamma rays from the radioactive decay of aluminum-26 produced in massive stars, confirmed this rate at approximately 1 to 2 core collapse supernovae per century in our galaxy. Yet we haven't witnessed one with the naked eye since the year 1604, when Johannes Kepler observed a brilliant new star in the constellation Ophiuchus. That 4-century drought isn't because supernovae have stopped occurring. It's because most of them happen in regions of the galaxy obscured from our view by dense clouds of interstellar dust. The violence continues, hidden from our eyes by cosmic curtains of debris. But supernovae, as spectacular as they are, represent only one entry in the universe's catalog of catastrophes. There are events far more energetic, far more violent, far more mysterious. Gamma-ray bursts, for instance, are the most powerful explosions known to occur in the cosmos. These brief, intense outbursts of high-energy radiation can erupt with a quintillion times the luminosity of our Sun. That's a 1 followed by 18 zeros. A single gamma-ray burst can release more energy in a few seconds than the Sun will emit across its entire lifetime of nuclear fusion. According to NASA, these events are now understood to announce the births of new black holes, created either when massive stars collapse at the end of their lives or when neutron stars collide with one another. The first gamma-ray burst was detected by accident in 1967 by the Vela satellites, which the United States had launched to monitor the Soviet Union for banned nuclear weapons tests. Instead of detecting signs of nuclear testing on Earth, these satellites picked up mysterious bursts of gamma radiation coming from deep space. For decades, the origin of these bursts remained one of astronomy's greatest mysteries. We now know they occur somewhere in the observable universe almost every day, brief flickers of unimaginable violence erupting across billions of light years. Then, there are the black holes themselves, those gravitational abysses from which nothing, not even light, can escape once it crosses the event horizon. The supermassive black holes lurking at the centers of most galaxies can contain masses equivalent to millions or even billions of suns. When an unlucky star wanders too close to one of these cosmic predators, it experiences what physicists call spaghettification, a wonderfully evocative term for a horrific process. The black hole's immense tidal forces stretch the star, pulling it apart into a thin stream of superheated matter that spirals inward like cosmic spaghetti being twirled onto a fork. These tidal disruption events, as astronomers call them, can produce brilliant flares of radiation that briefly outshine the entire surrounding galaxy. In October 2019, astronomers studying an event designated AT 2019 QI witnessed this process in unprecedented detail. Located just 215 million light-years from Earth in a spiral galaxy within the constellation Eridanus, it was the closest tidal disruption event ever recorded. Researchers observed as material was ejected at velocities up to 10,000 kilometers per second, fast enough to travel from Earth to the Moon in under 40 seconds. The star was essentially being shredded by invisible gravitational fingers. Its matter fed into a swirling accretion disk around the black hole, heated to millions of degrees, blazing with radiation across the electromagnetic spectrum. And yet, even as we catalog these violent phenomena, we must return to that fundamental paradox. This violence is generative. It creates as it destroys. The death of massive stars seeds the universe with heavy elements that would otherwise never exist. Supernovae explosions scatter elements like carbon, oxygen, silicon, and iron into the surrounding space, where they eventually coalesce into new stars, new planets, new possibilities for life. Even the heaviest elements, gold, platinum, uranium, require conditions so extreme that they can only be forged in the most cataclysmic events: the collision of neutron stars, the collapse of massive stellar cores, the death throes of the most extreme objects in existence. Research published in the journal Nature by Daniel Siegel and colleagues at the University of Guelph suggests that as much as 80% of these heavy R process elements may come from collapsers, a rare type of supernova produced when extremely massive stars, those around 30 times the mass of our Sun, collapse directly into black holes. The gold in a wedding ring, the platinum in medical equipment, the uranium that powers nuclear reactors, all of it was forged in cosmic catastrophes that occurred before our solar system formed, scattered through interstellar space by explosions that dwarfed anything human beings can produce. This is what we will explore together in the hours ahead. We will journey through the full spectrum of cosmic catastrophes, from the stellar explosions that seed galaxies with heavy elements to the gamma-ray bursts that could sterilize entire planets from billions of light years away. We will examine black hole collisions that send ripples through the fabric of space-time itself. We will investigate the slow-motion disaster of galactic collisions, where billions of stars are rearranged over hundreds of millions of years. We will consider the threats that loom over our own small world, the asteroids and comets that have shaped the history of life on Earth and could one day threaten our existence. And we will peer into the distant future, to the ultimate catastrophes that await the universe itself, the slow fade into heat death, the possible big rip that could tear apart the very atoms of existence. Along the way, we will discover how astronomers study these phenomena using telescopes that detect not just visible light, but X-rays, gamma rays, radio waves, and even gravitational waves, ripples in space-time first predicted by Einstein and finally detected in 2015 by the LIGO observatories. We will learn how these catastrophic events connect to one another in a vast cosmic cycle of destruction and renewal. And we will confront some of the deepest mysteries that remain unsolved, the questions that still puzzle scientists about the most extreme environments in the universe. The cosmos, it turns out, is far stranger and far more violent than our ancestors could have imagined when they first named the constellations and tracked the wandering planets across the sky. But it is also more beautiful, more profound, and more deeply connected to our own existence than they ever dreamed. Every sunset you have ever watched contains light filtered through an atmosphere made possible by stellar explosions. Every breath you take contains atoms that were once part of a star. Every beat of your heart is powered by iron that was forged in nuclear furnaces that no longer exist, scattered across space by catastrophes that occurred before the sun was born. So let us begin our exploration of these cosmic catastrophes with open minds and a sense of wonder. The universe may be violent beyond measure, but that violence has given rise to everything we know, everything we are, and everything we might yet become. In the death of stars, we find the birth of worlds. In the collision of neutron stars, we find the gold in our jewelry and the elements that allow complex chemistry to exist. In the chaos of cosmic destruction, we find the raw materials for life itself. The night sky is not peaceful. It is a theater of ongoing catastrophes separated from us by the merciful distances of space and the incomprehensible stretches of cosmic time. And understanding those catastrophes, the mysteries behind them, the physics that drives them, the consequences they create, is one of the great adventures of human knowledge. Let's begin that adventure now. There's an ancient Chinese term that captures the wonder our ancestors felt when a star suddenly appeared where none had been before. Guest star. For observers in imperial courts across Asia, these transient visitors to the heavens were portents of profound significance, omens of change, harbingers of dynasty and disaster. What they could not have known, gazing upward without telescopes or spectroscopes, was that these guest stars represented the most violent deaths in the universe. They were witnessing, from across thousands of light years, the explosive annihilation of stellar furnaces that had burned for millions of years. Today, we call these events supernovae. and understanding them has become one of the central quests of modern astrophysics. A supernova is not merely the death of a star, it is a cosmic announcement, a blaze of fury that briefly outshines billions of suns and seeds the universe with the raw materials for future worlds. In those few seconds or weeks of brilliance, a supernova can release more energy than our sun will produce across its entire 10 billion-year lifetime. And in the process, it manufactures and distributes the very elements that make planets, life, and consciousness possible. The brightest and most thoroughly documented guest star in recorded history blazed forth on July 4, 1054. Chinese astronomers at the court of the Song dynasty noted a brilliant new star appearing in the constellation we now call Taurus, positioned near the star Zeta Tauri. According to their meticulous records, this guest star was visible in broad daylight for 23 consecutive days, a remarkable feat that suggests it shone with the intensity of roughly 4 times the brightness of Venus at its most luminous, or perhaps magnitude -6. Japanese observers recorded it as well, and some scholars believe petroglyphs created by ancestral Puebloan peoples in the American Southwest may depict this same celestial spectacle, showing a bright star beside a crescent moon, which is precisely where the moon would have appeared on the morning of July 5, 1054, as viewed from New Mexico. This guest star remained visible to the naked eye for nearly 2 years before fading from view. What those medieval observers could never have imagined is that we can still see the aftermath of this explosion today. Through modern telescopes, we observe the Crab Nebula, a 6 light-year wide cloud of expanding debris located approximately 6,500 light-years from Earth. This glowing remnant, catalogued as Messier 1 or M1, was the first entry in Charles Messier's famous catalog of nebulous objects. At its heart spins a pulsar, the collapsed core of the original star, rotating roughly 30 times per second and emitting beams of radiation like a cosmic lighthouse. The Crab pulsar remains one of the most studied objects in the sky, a testament to the violence that created it nearly 1,000 years ago. 5 centuries after the guest star of 1054 faded from view, 2 more supernovae appeared in European skies, forever changing humanity's understanding of the cosmos. On November 11, 1572, the Danish astronomer Tycho Brahe observed a brilliant new star in the constellation Cassiopeia. Brahe was not the only observer. Records suggest others noticed the new star as early as August, but his meticulous measurements made this event famous. The supernova, now designated SN 1572, reached an apparent magnitude of approximately -4, rivaling Venus in brightness and visible during daylight hours for about 2 weeks. It remained visible to the naked eye until March 1574. What made Tycho's observations revolutionary was not simply that he recorded a new star, but that he demonstrated conclusively that this object lay far beyond the moon. By failing to detect any parallax shift, any change in the star's apparent position as Earth moved through space, Tycho proved the new star existed among the fixed stars, in a realm that Aristotelian cosmology insisted was eternal and unchangeable. The heavens, it turned out, were not perfect and immutable. Stars could be born, and stars could die. This observation helped crack open the rigid cosmological framework that had dominated European thought for centuries, paving the way for the astronomical revolution that Copernicus had begun, and Kepler and Galileo would continue. Just 32 years later, another supernova appeared, this time in the constellation Ophiuchus. The astronomer Johannes Kepler, working in Prague, began systematic observations on October 17, 1604, and tracked the new star for over a year, inspired by Tycho's earlier work. SN 1604, now called Kepler's supernova, reached a peak brightness of approximately magnitude -2, outshining Jupiter and remaining visible during daylight for 3 weeks. Italian astronomer Lodovico della Colombe had actually spotted it first on October 9th, but Kepler's detailed study gave the supernova its name. The astronomical tables of the time had predicted a conjunction between Mars and Jupiter, and some observers initially conflated the supernova with this auspicious alignment. Kepler himself published an entire book about the phenomenon in 1606, titled De Stella Nova, on the new star. Remarkably, SN 1604 remains the most recent supernova observed with certainty by the naked eye in our Milky Way galaxy. More than 4 centuries have passed without another such spectacle gracing our skies. This is not because supernovae have stopped occurring. They haven't. The Milky Way experiences core collapse supernovae at a rate of roughly 1 to 2 per century. But most of these explosions occur in distant arms of our spiral galaxy, obscured from view by the vast clouds of dust and gas that pervade the galactic disk. We know supernovae continue to occur because we detect their radioactive signatures. The European Space Agency's integral satellite has measured gamma rays from the decay of aluminum-26, a radioactive isotope produced in massive stars, and these measurements confirm the expected supernova rate. We also occasionally detect supernova remnants, expanding shells of debris like the Crab Nebula that reveal explosions occurred even when no contemporary records exist. But what exactly causes a supernova? The answer depends on what type of supernova you're discussing, because astronomers have identified 2 fundamentally different mechanisms that produce these stellar explosions. The first mechanism operates in massive stars, those born with at least 8 times the mass of our Sun, and sometimes far more. These stellar giants live fast and die young compared to smaller stars like our Sun. Where our Sun will burn steadily for roughly 10 billion years, a star 20 times as massive might exhaust its fuel in just 10 million years. This accelerated timeline occurs because massive stars must generate far more energy to counteract their crushing gravitational weight. They burn through their hydrogen fuel at a prodigious rate, fusing it into helium in their cores at temperatures exceeding 15 million degrees. When the hydrogen runs out, gravity compresses the core until temperatures rise high enough to ignite helium fusion, producing carbon and oxygen. As helium is exhausted, the core contracts again, heating further, and carbon fusion begins. This cascade continues through neon burning, oxygen burning, and finally silicon burning, each stage requiring higher temperatures and producing heavier elements. The star develops an onion-like structure with concentric shells of different elements being fused at different depths. At the outermost layers, hydrogen still burns. Deeper in, helium is consumed. Deeper still, carbon, then neon, then oxygen, then silicon. The entire sequence from carbon ignition to silicon exhaustion happens with startling speed by astronomical standards. Carbon burning might last 1,000 years. Neon burning lasts perhaps a year. Oxygen burning, months. Silicon burning, merely days. And then the process hits a wall. Silicon fusion produces iron group elements, iron, nickel, cobalt. And here, the cosmic engine stalls. Iron is the most tightly bound nucleus in nature. Fusing iron doesn't release energy, it absorbs energy. There is no more fuel to burn, no more nuclear fire to resist gravity's inexorable pull. What happens next unfolds in less than a second. The iron core, now containing roughly 1.4 solar masses of material compressed into a sphere the size of Earth, can no longer support itself. Electron degeneracy pressure, the quantum mechanical force that had been holding the core up, fails as electrons are captured by protons, producing neutrons and neutrinos. The core collapses at roughly 23% of the speed of light, falling inward upon itself. Temperatures spike to 100 billion Kelvin, 10,000 times hotter than the center of the Sun. The density exceeds that of an atomic nucleus. In that fraction of a second, the inner core, suddenly transformed into a ball of neutrons about 20 kilometers across, reaches nuclear densities and bounces. The implosion becomes an explosion. A shock wave races outward through the infouling material, heated by a flood of neutrinos so intense that, despite their incredibly weak interaction with matter, they deposit enough energy in the surrounding material to blow the star apart. In approximately 10 seconds, the collapsing core releases some 10 to the 46 joules of energy in neutrinos alone, roughly 100 times more energy than the Sun will emit across its entire lifetime. Only about 1% of this energy goes into the visible explosion. The rest streams away as neutrinos, invisible to most detectors. The The outward racing shock wave triggers a new wave of nuclear reactions in the stellar material it encounters. Temperatures and densities in the shock's wake are so extreme that nucleosynthesis occurs, the synthesis of new atomic nuclei. Elements that the star could not produce during its lifetime are forged in these final seconds. Iron peak elements like iron 56, cobalt 59, and nickel 58 are produced in abundance. The shock also creates conditions for the rapid neutron capture process, or R process, in which atomic nuclei are bombarded with free neutrons faster than they can undergo radioactive decay. This R process builds the heaviest elements, gold, platinum, uranium, and beyond. What remains after the explosion depends on the mass of the core. If the remaining core is less than about 2 to 3 solar masses, the precise limit is still debated but is known as the Tolman-Oppenheimer-Volkoff limit. The collapse halts when neutron degeneracy pressure and nuclear forces balance gravity. The result is a neutron star, a city-sized remnant with the mass of the Sun compressed into a sphere perhaps 20 kilometers in diameter. The density is almost inconceivable. A sugar cube-sized sample of neutron star material would weigh roughly 1 billion tons. If the core is more massive, not even neutron degeneracy pressure can halt the collapse. The core continues shrinking until it forms a black hole, vanishing behind an event horizon from which nothing, not even light, can escape. This core collapse mechanism produces what astronomers classify as Type II supernovae, along with the related Type 1b and Type 1c supernovae. The classification is based on the spectra of the explosion, the chemical fingerprints of elements detected in the expanding debris. Type II supernovae show hydrogen in their spectra, indicating the exploding star still possessed its outer hydrogen envelope. Type 1b supernovae lack hydrogen but show helium, suggesting the star lost its hydrogen layers before exploding, perhaps through powerful stellar winds or mass transfer to a binary companion. Type 1c supernovae lack both hydrogen and helium, indicating the star was stripped down nearly to its bare core before the end came. These stripped envelope supernovae are thought to occur in Wolf-Rayet stars, massive and luminous objects that have blown away their outer layers through fierce stellar winds. The second major mechanism for producing supernovae operates through an entirely different channel and involves an entirely different type of star. Type 1a supernovae do not arise from the deaths of massive stars. Instead, they occur when white dwarf stars, the dense Earth-sized remnants of Sun-like stars, undergo runaway thermonuclear explosions. A white dwarf is what remains after a star like our Sun exhausts its nuclear fuel. Too small to ignite carbon fusion in its core, it sheds its outer layers as a beautiful planetary nebula and collapses into a compact object supported by electron degeneracy pressure. The typical white dwarf contains about 60% of the original star's mass, squeezed into a volume comparable to Earth. These stellar cinders are incredibly stable and can persist for billions of years, slowly cooling and fading. But a white dwarf in a binary system, orbiting a companion star, can meet a very different fate. If the companion is a normal star that evolves and expands, mass can flow from the companion onto the white dwarf. This process, called accretion, gradually increases the white dwarf's mass. As it approaches the Chandrasekhar limit, approximately 1.44 solar masses, named after the physicist Subrahmanyan Chandrasekhar who calculated it, something dramatic happens. The compression at the core raises temperatures to the point where carbon fusion ignites. Unlike in a normal star, where the increasing temperature causes expansion and cooling that regulates the nuclear reaction, a white dwarf cannot expand. The electron degeneracy pressure that supports it doesn't depend on temperature in the same way. When carbon ignites, there is no safety valve. The temperature rises, which accelerates the fusion rate, which raises the temperature further, which accelerates the fusion even more. A thermonuclear runaway ensues. Within approximately 1 second, a substantial fraction of the white dwarf's mass undergoes fusion, releasing roughly 10 to the 44 joules of energy, enough to unbind the entire star. The white dwarf is completely obliterated, leaving no remnant behind. This total destruction distinguishes Type 1a supernovae from core collapse supernovae, which always leave behind a neutron star or black hole. Type 1a explosions synthesize enormous quantities of radioactive nickel-56, which decays first to cobalt-56 and then to stable iron-56. This radioactive decay powers the optical emission of the supernova, causing it to brighten to a peak over roughly 3 weeks and then gradually fade as the radioactive fuel is consumed. Because all Type 1a supernovae occur in white dwarfs of approximately the same mass, right at the Chandrasekhar limit, they all release approximately the same amount of energy. This remarkable uniformity has made them invaluable as standard candles for measuring cosmic distances. Observations of Type 1a supernovae in distant galaxies led to the 1998 discovery that the expansion of the universe is accelerating, a finding that earned Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011. There is also an alternative pathway to Type 1a supernovae, the collision and merger of two white dwarfs. In a tight binary system containing two white dwarfs, gravitational wave emission can cause the orbit to shrink over billions of years until the two objects spiral together and merge. If their combined mass exceeds the Chandrasekhar limit, the result is the same: thermonuclear detonation. Studies using data from the Sloan Digital Sky Survey found approximately 15 double white dwarf systems among 4,000 white dwarfs examined, suggesting that white dwarf mergers could occur roughly once per century in the Milky Way, a rate consistent with the observed frequency of Type 1a supernovae. The nucleosynthesis occurring in supernovae is crucial for the chemical evolution of the universe. When the cosmos emerged from the Big Bang, it contained essentially only hydrogen, helium, and trace amounts of lithium. Every other element, every atom of carbon, oxygen, nitrogen, calcium, iron, and beyond, was manufactured inside stars and distributed through stellar explosions. The elements up to the iron peak are produced through successive stages of nuclear burning in massive stars and through explosive nucleosynthesis during the supernova itself. Elements heavier than iron require different processes. The slow neutron capture process, or S process, occurs in certain giant stars, where seed nuclei gradually capture neutrons one at a time, with sufficient time between captures for radioactive decay to occur if the resulting nucleus is unstable. This process builds up elements like strontium, barium, and lead over thousands of years in stellar interiors. The rapid neutron capture process, or R process, requires conditions so extreme that neutron captures happen faster than radioactive decay. This can only occur in environments with extraordinarily high neutron fluxes, the collapsed cores of supernovae, the material ejected from neutron star collisions, or possibly the winds blowing off newly formed neutron stars. The R process builds the heaviest elements in nature: gold, platinum, uranium, thorium. These atoms are forged in seconds during the most violent events in the cosmos and then scattered into space, eventually becoming incorporated into new generations of stars, planets, and living beings. The February 1987 detection of supernova 1987A in the Large Magellanic Cloud marked a watershed moment in supernova science. Located approximately 168,000 light-years from Earth in a dwarf galaxy visible from the southern hemisphere, this was the closest observed supernova since Kepler's supernova 383 years earlier. For the first time, astronomers could study a supernova with modern instruments across the entire electromagnetic spectrum. But perhaps the most significant detection came not from photons, but from neutrinos. Approximately 3 hours before visible light from SN 1987A reached Earth, neutrino detectors around the world registered a brief burst of these ghostly particles. The Kamiokande 2 detector in Japan detected 12 antineutrinos. The IMB detector in Ohio detected 8. The Baksan detector in Russia detected 5. These 25 neutrinos, arriving within a span of less than 13 seconds, represented the first direct detection of neutrinos from a supernova. confirming theoretical models that predicted 99% of the energy released in a core collapse emerges as neutrinos rather than light. This observation marked the birth of neutrino astronomy and opened an entirely new window on the universe. The progenitor star of SN 1987A was identified in pre-explosion images as Sandalik -69 degrees 202, a blue supergiant with roughly 20 solar masses. This was initially puzzling because theoretical models had predicted that core collapse supernovae should arise from red supergiants. The unexpected blue color of the progenitor led to revisions in stellar evolution models and a deeper understanding of how massive stars behave in the final stages of their lives. Supernovae are also the primary sources of cosmic rays, high-energy particles, mostly protons and atomic nuclei, that stream through the galaxy at nearly the speed of light. The shock waves from supernova explosions accelerate particles to tremendous energies through a process called diffusive shock acceleration or Fermi acceleration. These cosmic rays carry more energy per particle than any human-made accelerator can achieve and constantly bombard Earth's atmosphere, producing cascades of secondary particles. Some cosmic ray protons carry 10 to the 20 electron volts of energy, the kinetic energy of a baseball thrown at professional speeds, concentrated in a single subatomic particle. As we peer into the night sky, we cannot predict when the next Milky Way supernova visible to the naked eye will occur. It could happen tomorrow. It could be decades away. Astronomers monitor candidate stars, massive, evolved objects that appear to be in the final stages of their lives. But the precise timing of core collapse is impossible to forecast. Betelgeuse, the red supergiant marking the shoulder of Orion, has drawn particular attention because it visibly dimmed in late 2019 and early 2020, sparking speculation about its impending death. Observations ultimately attributed the dimming to dust ejected by the star and cooling of its surface rather than imminent explosion. Betelgeuse will indeed explode someday, perhaps in the next 100,000 years, but probably not in our lifetimes. When the next nearby supernova does occur, modern neutrino detectors will likely provide hours of advance warning before visible light arrives. The Super Kamiokande detector in Japan, capable of detecting thousands of neutrinos from a galactic supernova, continuously monitors for just such an event. The Supernova Early Warning System, or SNEWS, links neutrino detectors around the world to provide rapid alerts to the astronomical community. When the neutrino burst arrives, astronomers will race to train every available telescope on the sky, hoping to catch the first optical light and record every phase of the explosion in unprecedented detail. For now, we content ourselves with observing supernovae in distant galaxies. Several hundred are discovered each year, and studying the remnants of ancient explosions in our own Milky Way. In these expanding shells of debris, we find direct evidence of the elements forged in stellar explosions. We map the distribution of oxygen and iron, silicon and sulfur. We trace the shock waves still propagating outward millennia after the initial explosion. And in every observation, we gather new clues about the processes that created the atoms comprising our world. Supernovae remind us that the universe operates on timescales and energy scales utterly beyond human experience. A single star, dying in a fraction of a second, can outshine 10 billion suns and scatter elements across light years of space. The violence is total, the destruction complete, and yet, from that destruction comes creation. The debris of ancient supernovae became the nebulae from which new stars and planets formed. The iron core of our Earth, the oxygen in our atmosphere, the calcium in our bones, all of it was forged in the death throes of massive stars billions of years ago. We are, quite literally, children of the supernovae. On July 2, 1967, at precisely 14:19 Universal Time, something remarkable happened aboard a pair of American military satellites orbiting high above Earth. The Vela 3 and Vela 4 spacecraft, designed to detect the gamma radiation signature of clandestine Soviet nuclear weapons tests in space, registered an intense flash of gamma rays. The signature was utterly unlike any nuclear weapon. There was no characteristic double pulse profile of an atomic detonation, no gradual radioactive decay curve. Instead, the instruments recorded something mysterious: a sharp spike, a dip, a second spike, and then a long, gradual tail-off of gamma radiation coming from somewhere far beyond Earth's atmosphere. Ray Klibosatl and his team at the Los Alamos National Laboratory, tasked with analyzing Vela data, filed the observation away. It wasn't urgent, clearly not a nuclear test, clearly not from Earth. But it was strange. As subsequent Vela satellites launched with improved instruments, more of these puzzling gamma-ray bursts appeared in the data. By analyzing the arrival times at multiple satellites spread across the solar system, the Los Alamos team began to triangulate rough positions in the sky. The bursts were coming from every direction, randomly distributed across the celestial sphere. They were not from the sun, not from any known solar system object, and almost certainly not from within our galaxy. The findings were declassified and published in 1973 in a brief paper in the Astrophysical Journal Letters, titled "Observations of Gamma-Ray Bursts of Cosmic Origin." The paper described 16 events and speculated about possible origins. It marked the beginning of one of the longest-running mysteries in astrophysics, a puzzle that would take 3 decades to solve and would reveal the existence of the most powerful explosions in the universe since the Big Bang itself. Gamma-ray bursts, or GRBs, are exactly what their name suggests: sudden, intense flashes of gamma radiation appearing from random directions in space. They typically last from milliseconds to several minutes, though the afterglows that follow can persist for days or weeks at longer wavelengths. During their brief peak, gamma-ray bursts can outshine everything else in the gamma-ray sky combined. They are, without exaggeration, the brightest electromagnetic events in the known universe. The energy involved defies comprehension. A typical long-duration gamma-ray burst releases approximately 10 to the 52 to 10 to the 54 ergs of energy in just a few seconds. That's roughly the amount of energy our sun will emit across its entire 10 billion-year lifetime, compressed into a cosmic instant. If a gamma-ray burst were somehow isotropic, emitting equally in all directions, it would briefly outshine the entire observable universe. We can detect these events from billions of light-years away because of their staggering luminosity. For 2 decades after their discovery, gamma-ray bursts remained profoundly mysterious. Astronomers detected them regularly. The Burst and Transient Source experiment aboard NASA's Compton Gamma Ray Observatory cataloged nearly 3,000 between 1991 and 2000, averaging about 1 per day. The bursts came from every direction with no clustering toward the plane of the Milky Way or any other structure. This isotropy strongly suggested they originated outside our galaxy, at cosmological distances, but without identifying the host galaxies, no one could be certain. More than 100 different theoretical models were proposed to explain gamma-ray bursts: colliding neutron stars, exotic forms of stellar explosions, quakes on neutron star surfaces, evaporating primordial black holes, cosmic strings, antimatter comets striking stars. The possibilities seemed endless, and the data was insufficient to discriminate among them. The breakthrough came in February 1997, when the Italian-Dutch satellite Bepo-SAX detected GRB 970228 and rapidly provided an accurate position. Within hours, ground-based telescopes imaged the location and found a fading optical source, the afterglow of the explosion. Deeper images revealed a faint, distant host galaxy. For the first time, astronomers had linked a gamma-ray burst to a specific cosmic location. Subsequent observations of GRB 970508 in May 1997 allowed spectroscopic measurement of the host galaxy's redshift, 0.835, corresponding to a distance of roughly 6 billion light-years. The cosmological origin of gamma-ray bursts was confirmed. They were indeed the most distant, most luminous explosions ever detected. With positions in hand, astronomers could finally study gamma-ray bursts systematically. They discovered that the population naturally divides into 2 classes based on duration: Short gamma-ray bursts last less than about 2 seconds and tend to have harder, higher energy spectra. Long gamma-ray bursts persist for anywhere from 2 seconds to several minutes, and occasionally much longer, and display softer spectra. These two populations, it turned out, arise from completely different physical mechanisms. Long gamma-ray bursts are associated with the deaths of extremely massive stars, the cosmic catastrophes we now call hypernovae or collapsers. The term hypernova was coined in the late 1990s to describe stellar explosions significantly more energetic than ordinary supernovae, typically releasing kinetic energy an order of magnitude greater, around 10 to the 45 joules or more. Polish astronomer Bohdan Paczynski hypothesized that rapidly spinning massive stars could produce such events, and Stan Woosley of the University of California, Santa Cruz, developed the detailed collapsar model to explain them. In the collapsar model, a star with an initial mass exceeding roughly 25 to 30 solar masses reaches the end of its nuclear fuel reserves. But unlike in an ordinary core collapse supernova, the star's core is massive enough and rotating rapidly enough that a black hole forms almost immediately during the collapse, rather than a neutron star. The infalling stellar material doesn't simply crash onto the black hole. Because of its angular momentum, it forms a swirling accretion disk around the newborn black hole. This disk is extraordinarily hot and dense, heated by friction and gravitational compression to temperatures of billions of degrees. Through mechanisms that remain subjects of active research, likely involving powerful magnetic fields threading the disk and the black hole's rotation, a fraction of the infalling energy is channeled into two narrow jets of relativistic plasma, material moving at 99.9% or more of the speed of light. These jets blast outward along the black hole's rotation axis, punching through the overlying stellar material. If the star has retained its extended hydrogen envelope, the jets may stall and fail to produce an observable gamma-ray burst. But if the star has been stripped of its outer layers, becoming what astronomers call a Wolf-Rayet star, the jets can break free of the stellar surface and continue into space. It is these jets that produce the observed gamma-ray emission. As the jet material plows through the interstellar medium or interacts with itself through internal shocks, particles are accelerated to extreme energies, and gamma rays are produced through synchrotron radiation and inverse Compton scattering. Because the jets are highly collimated, focused into cones of perhaps 5 to 10 degrees, we only detect gamma-ray bursts when a jet happens to point toward Earth. For every gamma-ray burst we observe, there may be dozens or hundreds of similar events whose jets point elsewhere, invisible to us. The connection between long gamma-ray bursts and hypernovae was definitively established through observations of several nearby events. GRB 980425, detected on April 25, 1998, was associated with the supernova SN 1998 BW in a spiral galaxy about 140 million light-years away. This supernova was extraordinarily luminous, roughly 100 times brighter than a typical Type 1b supernova, with spectral lines indicating expansion velocities up to 60,000 kilometers per second, far faster than normal supernovae. The gamma-ray burst itself was peculiar, far less luminous than typical cosmological GRBs, but the association was compelling. The conclusive proof came with GRB A030329 in March 2003. This burst occurred at a distance of approximately 2.65 billion light-years and was observed in unprecedented detail by ESO's Very Large Telescope. Over the following weeks, as the gamma-ray afterglow faded, the underlying supernova, designated SN 2003DH, became visible in the spectra. The supernova signature was unmistakable, broad spectral features indicating extremely high expansion velocities, consistent with a hypernova explosion. The timing matched perfectly. The supernova explosion and the gamma-ray burst occurred simultaneously within measurement uncertainties. The collapsar model had been confirmed. Since then, numerous gamma-ray bursts have been linked to underlying supernovae, solidifying our understanding that long GRBs represent a particular channel of stellar death. Not all massive stars produce gamma-ray bursts. The conditions must be just right, with rapid rotation, low metallicity, which reduces mass loss through stellar winds and helps preserve angular momentum, and perhaps particular binary interactions. But when those conditions align, the result is the most violent explosion the universe can produce through stellar means. The most extreme gamma-ray burst ever detected arrived at Earth on October 9, 2022. Designated GRB 2109A and nicknamed the BOAT, the brightest of all time, this event originated roughly 2.4 billion light-years away in the direction of the constellation Sagitta. It was so luminous that it saturated gamma-ray detectors and even affected Earth's ionosphere, measurably disturbing the upper atmosphere despite originating billions of light-years distant. The burst lasted over 600 seconds, more than 10 minutes, and released an estimated 10 to the 54 ergs of isotropic equivalent energy. This made it roughly 70 times brighter than the second brightest gamma-ray burst ever observed. Astrophysicists estimated such an event might occur only once every 10,000 years within detectable range. The underlying supernova was subsequently identified, confirming the collapsor connection once again. Short gamma-ray bursts arise through an entirely different mechanism, the collision and merger of compact objects. When two neutron stars, or a neutron star and a black hole, spiral together after billions of years of orbital decay, they eventually merge in a cataclysmic event lasting only milliseconds. The merger produces intense gravitational waves, ripples in spacetime itself, along with a short burst of gamma rays as material is ejected and jets are launched. The connection between short GRBs and neutron star mergers was spectacularly confirmed on August 17, 2017, when the LIGO and Virgo gravitational wave detectors observed an event designated GWM70817. The gravitational wave signal showed the characteristic pattern of two inspiraling neutron stars with masses of approximately 1.1 to 1.6 solar masses each. Just 1.7 seconds after the merger, the Fermi Gamma Ray Space Telescope detected a short gamma-ray burst from the same direction, designated GRB 19807A. This was the first time gravitational waves and electromagnetic radiation had been detected from the same astrophysical event, inaugurating the era of multi-messenger astronomy. The slight delay between the gravitational waves and the gamma rays, approximately 1.7 seconds, confirmed Einstein's prediction that gravitational waves travel at the speed of light to extraordinary precision. The merged object likely collapsed into a black hole within milliseconds, launching jets that produced the observed gamma-ray emission. However, unlike most short GRBs, GRB 170817A was observed somewhat off-axis, meaning Earth was not directly in the path of the primary jet, which partially explains its relatively modest brightness compared to cosmological short bursts. Following GW 170817, astronomers observed an extraordinary phenomenon, a kilonova, the radioactive glow of heavy elements freshly synthesized in the merger debris. We will discuss kilonovae in detail in the next section, but for now, it's worth noting that this observation confirmed short gamma-ray bursts arise from neutron star mergers, events that also serve as cosmic forges for the heaviest elements in the periodic table. The potential danger of gamma-ray bursts to life on Earth has been seriously considered by astrobiologists. If a gamma-ray burst were to occur within our galaxy, with its jet aimed at Earth, the consequences could be catastrophic. The initial gamma radiation would not penetrate to the surface. Earth's atmosphere effectively shields us from cosmic gamma rays. But the high-energy photons would interact with atmospheric nitrogen and oxygen, generating nitrogen oxides that would severely deplete the ozone layer. With the ozone shield compromised, deadly ultraviolet radiation from the sun would reach the surface, devastating ecosystems and potentially causing a mass extinction. Some researchers have proposed that a gamma-ray burst may have been responsible for the Ordovician-Silurian extinction approximately 450 million years ago, when roughly 85% of marine species disappeared. The evidence is circumstantial. We cannot prove a gamma-ray burst occurred, but the extinction pattern, with organisms in shallow waters suffering disproportionately compared to deep-sea creatures protected from ultraviolet radiation, is consistent with intense UV exposure following ozone depletion. Fortunately, the threat appears relatively low. Most gamma-ray bursts originate in distant galaxies, and the beaming effect means only jets pointed directly at Earth could cause harm. Long gamma-ray bursts preferentially occur in low metallicity environments, and the Milky Way's disk, enriched by billions of years of stellar nucleosynthesis, may be inhospitable to the specific conditions that produce collapsers. Short gamma-ray bursts from neutron star mergers could theoretically occur nearby, but the rate is estimated at roughly 1 per 100 million years within dangerous range. We are probably safe, though the universe occasionally reminds us that probably is not a guarantee. The study of gamma-ray bursts has revolutionized our understanding of stellar deaths and compact object physics. These events probe the most extreme conditions in the universe, the formation of black holes in real time, the acceleration of particles to near-light speed, the generation of magnetic fields billions of times stronger than Earth's. Each gamma-ray burst is a laboratory for high-energy physics operating at energies far beyond any terrestrial accelerator. Current and future observatories continue to expand our view. NASA's SWIFT observatory, launched in 2004, can rapidly slew to detect gamma-ray burst afterglows across multiple wavelengths. The Fermi Gamma-Ray Space Telescope provides continuous monitoring of the gamma-ray sky. Ground-based robotic telescopes respond to alerts within seconds, imaging afterglows before they fade. Plans are underway for next-generation instruments with even greater sensitivity and faster response times. Perhaps most exciting is the prospect of coordinated observations combining gravitational waves and electromagnetic radiation. The detection of GW178.7 was just the beginning. As gravitational wave detectors improve, with the addition of KAGRA in Japan, the planned LIGO India, and eventual space-based detectors like LISA, we will observe more neutron star mergers, more short gamma-ray bursts, more opportunities to understand these remarkable events from multiple perspectives simultaneously. Gamma-ray bursts represent the universe at its most extreme. Titanic explosions marking the births of black holes, the collisions of stellar corpses, the release of energies that dwarf anything else in the observable cosmos. They are rare, brief, and unpredictable, appearing anywhere in the sky without warning. Yet, in their fleeting brilliance, they illuminate fundamental physics and remind us that the universe, for all its apparent serenity, remains capable of violence beyond imagining. When the Vela satellites first detected that puzzling flash in 1967, their operators could not have imagined what they had discovered. What seemed like noise, like an unexplained anomaly in military surveillance data, turned out to be the signature of the most powerful explosions since the Big Bang itself. Science, it seems, has a way of revealing wonders in unexpected places. There is gold on your finger if you wear a wedding band. There is platinum in your catalytic converter if you drive a car. There is uranium deep in the Earth's crust, slowly decaying and generating the heat that drives plate tectonics. These elements seem mundane, familiar, part of the background furniture of existence. And yet they are also profoundly mysterious, because for decades, astrophysicists could not explain where they came from. The problem was this: ordinary supernovae, as we discussed, produce elements up through the iron peak, iron, cobalt, nickel, through explosive nucleosynthesis. Some heavier elements can be produced through the slow neutron capture process in the quiet interiors of aging giant stars. But the heaviest elements, those beyond bismuth in the periodic table, require conditions so extreme that they can only be forged through the rapid neutron capture process, the R process. This requires an environment flooded with free neutrons at densities exceeding 10 to the 24 neutrons per cubic centimeter, a gram of neutrons in every cubic centimeter of space, at temperatures around 1 billion degrees. Where in the universe could such conditions exist? For many years, the leading candidate was core collapse supernovae. The collapsing cores of massive stars, just before they bounce and explode, are indeed extraordinarily neutron-rich. But detailed computational models struggled to produce the observed abundances of our process elements through this mechanism alone. The numbers didn't quite add up. Something was missing from the picture. The answer, it turned out, was hiding in one of the most violent events the universe can produce: the collision and merger of neutron stars. Neutron stars are the compressed cores left behind when massive stars explode as supernovae. They contain approximately 1.4 to 2 solar masses of material squeezed into a sphere roughly 20 kilometers in diameter, the size of a city, yet containing more mass than our sun. The density is almost incomprehensible. A sugar cube's worth of neutron star material would weigh approximately 1 billion tons. At such densities, atoms cannot exist. Electrons are crushed into protons to form neutrons, and the entire star becomes essentially one giant atomic nucleus, held together by gravity and supported against further collapse by neutron degeneracy pressure and nuclear forces. When two neutron stars form in a binary system, perhaps from two massive stars that were born together, both of which underwent supernova explosions, they begin a slow death spiral. According to Einstein's general relativity, accelerating masses emit gravitational waves, ripples in the fabric of space-time that carry energy away from the system. As this energy is radiated away, the two neutron stars gradually spiral closer to one another. The process is exceedingly slow at first. In the Hulse-Taylor binary pulsar, discovered in 1974 and earning Russell Hulse and Joseph Taylor the Nobel Prize in 1993, the two neutron stars are approaching each other by roughly 3.5 meters per year. At that rate, they will merge in approximately 300 million years. But as the neutron stars draw closer, the orbital decay accelerates, the gravitational wave emission intensifies. In the final seconds before merger, the two objects are whipping around each other at a significant fraction of the speed of light, completing dozens of orbits per second. The gravitational waves produced in these final moments are powerful enough to be detected by instruments here on Earth, the Laser Interferometer Gravitational Wave Observatory, or LIGO, and its European counterpart, Virgo. The first direct detection of gravitational waves occurred on September 14, 2015, when LIGO observed the merger of two black holes approximately 1.3 billion light-years from Earth. This achievement earned Rainer Weiss, Kip Thorne, and Barry Barish the 2017 Nobel Prize in Physics. But for understanding the R process and the origin of heavy elements, a different type of merger was needed. Not black holes, which swallow everything and produce no electromagnetic signal, but neutron stars, which would spray their neutron-rich material across space in the violence of collision. That observation came on August 17, 2017, with the detection of GW 170.17. At 12:41:04 Coordinated Universal Time, the gravitational wave signal arrived at LIGO's two detectors in Hanford, Washington, and Livingston, Louisiana, followed a fraction of a second later by the Virgo detector in Italy. The signal was different from the black hole mergers observed before. It lasted approximately 100 seconds, far longer than the brief chirp of merging black holes, because neutron stars, being less massive, spiral together more slowly in the final moments. The characteristic waveform revealed the masses of the two objects, approximately 1.1 to 1.6 solar masses each, consistent with neutron stars and inconsistent with black holes. Just 1.7 seconds after the gravitational waves from the final merger, the Fermi Gamma Ray Space Telescope detected a short gamma ray burst from the same direction. The European Space Agency's integral satellite confirmed the detection. This was the smoking gun. The same event had produced both gravitational waves and electromagnetic radiation. Multi-messenger astronomy, long theorized, had become reality. The slight delay between the gravitational waves and the gamma rays was fascinating in itself. Gravitational waves and light should travel at the same speed according to general relativity, and the 1.7-second delay for a source 130 million light-years away constrained any difference to fewer than a few parts in 10 to the 15, an extraordinarily precise confirmation of Einstein's theory. The delay was likely caused by the physics of the merger itself. It takes a moment for the post-merger object to settle, form an accretion disk, launch jets, and produce gamma rays. But the most remarkable observations were yet to come. In the hours and days following the merger, telescopes around the world turned toward the source, located in the Shell elliptical galaxy NGC 4993 in the constellation Hydra. What they observed was a kilonova, a term coined in 2010 by Brian Metzger, then a postdoctoral researcher at Princeton, to describe the optical and infrared transient expected from R-process nucleosynthesis in neutron star merger debris. A kilonova is not simply a smaller nova. The name refers to its luminosity being roughly 1,000 times that of a classical nova explosion. In a kilonova, the violence of the merger ejects a fraction of the neutron star material, perhaps 1 to 10% of a solar mass, into space at velocities of 10 to 30% the speed of light. This ejected material is extraordinarily neutron-rich, and as it expands and decompresses, the R process kicks in. Seed nuclei are bombarded with free neutrons at rates faster than radioactive decay can keep up. Heavy nuclei are built up in a matter of seconds, climbing the periodic table toward uranium, thorium, and even heavier transuranic elements that exist only briefly before decaying. The radioactive decay of these newly forged heavy elements generates enormous heat, which powers the kilonova's optical and infrared emission. Unlike a supernova, which shines for weeks primarily through radioactive nickel-56 decay, a kilonova evolves rapidly, peaking in brightness within about a day and fading over the following week or so. The color of the emission provides crucial information about the composition. Material rich in lanthanides, the series of elements from lanthanum to lutetium, produces a distinctive red or infrared glow because these elements have complex electron configurations that absorb blue light efficiently. The observations of AT 2017 GFO, the kilonova associated with GW170817, matched theoretical predictions remarkably well. In the first few hours, the kilonova appeared blue, suggesting emission from material with fewer heavy elements, perhaps ejected from the polar regions of the merger, where neutron-rich conditions were less extreme. Over the following days, the emission shifted to red as the lanthanide-rich material from the main ejecta began to dominate. Spectroscopic observations from the Gemini South and other telescopes revealed the fingerprints of heavy elements in the expanding debris. In October 2017, a team led by Stephen Smart reported detecting strontium in the kilonova spectra, the first identification of a specific R-process element in a kilonova. Later analyses identified additional elements. Researchers reported evidence for tellurium and possibly other heavy elements in the spectral data. The abundances were consistent with R-process nucleosynthesis models, confirming that neutron star mergers are indeed cosmic forges for the heaviest elements. Calculations suggested that the single merger event GW170817 produced several Earth masses worth of gold, 10 Earth masses of platinum, and substantial quantities of uranium and other actinides, all created in a matter of seconds and scattered into space to eventually become incorporated into new generations of stars and planets. This discovery resolved a long-standing puzzle about the origin of R-process elements. While supernovae may contribute some R-process material, neutron star mergers appear to be the dominant source, responsible for perhaps 80% or more of the heavy R-process elements in the universe. The golden jewelry, the platinum in industrial catalysts, the uranium in nuclear reactors, all of it was forged in ancient collisions of stellar corpses, violent events that occurred billions of years before our solar system formed. The physics of the merger itself is extraordinarily complex and remains an active area of research. When two neutron stars collide, the outcome depends on their total mass and the details of the equation of state, the relationship between pressure and density in neutron star matter, which is not precisely known. If the combined mass is below approximately 2.5 to 2.8 solar masses, the exact limit depends on uncertain nuclear physics. The merger may produce a hypermassive neutron star, a rapidly spinning object briefly supported against collapse by its own rotation. This hypermassive neutron star may survive for milliseconds to seconds before collapsing into a black hole. If the combined mass is above this threshold, a black hole forms almost immediately. In rare cases, if the masses are low enough, a stable or long-lived neutron star might survive the merger. For GW170817, the evidence suggests that a hypermassive neutron star formed initially and then collapsed into a black hole within a few seconds. Researchers analyzing the gravitational wave signal found subtle hints of post-merger oscillations consistent with a briefly surviving neutron star. The energy released by the magnetic fields of this spinning remnant may have powered the observed gamma-ray burst. Other researchers have proposed that a magnetar, a neutron star with an extraordinarily powerful magnetic field, may have survived for an extended period before collapsing, which could explain some features of the kilonova light curve. The merger also produced intense neutrino emission, though these neutrinos were not detected. The distance was simply too great for Earth's neutrino detectors to register more than a handful at most. The collision created a swirling accretion disk around the final black hole or neutron star, with material heated to billions of degrees. Some of this material was launched as relativistic jets along the polar axis, producing the observed short gamma-ray burst. The jets were oriented somewhat away from Earth's line of sight, which explains why GRB 170817A was relatively faint compared to typical short bursts viewed directly down the jet. The detection of GW170817 demonstrated the power of multi-messenger astronomy. Gravitational waves provided information about the masses and spins of the merging objects, the dynamics of the inspiral, and the moment of merger. The gamma-ray burst confirmed the connection to short GRBs and provided information about jet physics. The kilonova revealed the nucleosynthesis occurring in the ejecta. X-ray and radio observations over the following months tracked the interaction of the jet with surrounding material, providing additional constraints on the explosion geometry. Together, these observations told a far richer story than any single messenger could alone. Since GW170817, gravitational wave detectors have observed additional neutron star merger candidates, though none with such spectacular electromagnetic counterparts. GW190425, detected in April 2019, appeared to be another binary neutron star merger, with a combined mass of approximately 3.4 solar masses, unusually heavy compared to known neutron star binaries in the Milky Way. No electromagnetic counterpart was detected, possibly because the merger occurred at a greater distance or the ejecta were obscured, or perhaps because a black hole formed so quickly that little material was ejected. Astronomers have also identified candidate colonovae through other means without gravitational wave detection. GRB 13603b, a short gamma-ray burst in 2013, showed an infrared excess consistent with kilonova emission, predating the definitive GW107 detection by 4 years. GRB 2011a, observed in December 2021, presented an unusual case, a long-duration gamma-ray burst lasting roughly 50 seconds that nevertheless showed kilonova emission, suggesting it may have arisen from a neutron star merger rather than a collapsar, challenging the traditional classification of GRBs by duration. The cosmic implications of neutron star mergers extend beyond nucleosynthesis. These events contribute to the enrichment of galaxies with heavy elements, influencing the chemical evolution of stellar populations across cosmic time. The rate of neutron star mergers, estimated at 1 per 10,000 to 100,000 years per galaxy, means that over billions of years, the accumulated products of these collisions become incorporated into the interstellar medium, eventually finding their way into new stars, planets, and potentially life. There is a strange poetry in this connection. The gold atoms in a wedding ring, symbolizing commitment and connection, were created in an event that also represents connection in a cosmic sense. Two stellar corpses, once separate, spiraling together over billions of years until they finally merge in a cataclysm of light and gravity. The violence of the collision seeded space with the very materials that would later become part of our world. Every atom of gold in existence passed through such an event, forged in the fires of colliding neutron stars somewhere in the universe, sometime in the past 13.8 billion years. The era of multi-messenger astronomy has only just begun. As gravitational wave detectors improve in sensitivity, we will observe more neutron star mergers at greater distances. Future detectors, like the proposed Einstein telescope in Europe and Cosmic Explorer in the United States, will detect mergers throughout the observable universe. Space-based detectors like LISA will observe entirely different sources, supermassive black hole mergers, extreme mass ratio inspirals, and perhaps the gravitational wave background from the early universe. Each new detection will add to our understanding of these remarkable events. The final dance of stellar corpses, the birth of black holes, the cosmic alchemy that creates the heaviest elements. We have glimpsed for the first time the violent origin of the atoms that constitute our world, and in doing so, we have discovered that the universe creates its most precious materials through its most extreme violence. Nothing escapes a black hole, not light, not matter, not information, at least as far as classical physics is concerned. A black hole is the universe's ultimate dead end, a region of space-time so severely warped by gravity that everything falls in but nothing comes out. The boundary separating the inside from the outside is called the event horizon, not a physical surface, but a mathematical threshold beyond which escape velocity exceeds the speed of light, trapping everything forever. And yet, paradoxically, black holes are among the most luminous objects in the known universe. Not the black holes themselves, of course, but their immediate environments. As matter spirals into a black hole, it is compressed, heated, and accelerated to tremendous energies. Accretion disks around black holes can outshine entire galaxies. Jets of plasma launched from near the event horizon travel at nearly the speed of light and extend for thousands of light years. The catastrophic feeding of black holes produces some of the most spectacular phenomena in astrophysics. Black holes come in at least 3 distinct classes, defined by their masses and consequently their origins. Stellar mass black holes form from the deaths of massive stars. When a star more than approximately 20 to 25 times the mass of the Sun exhausts its nuclear fuel and undergoes core collapse, the resulting supernova may leave behind not a neutron star but a black hole. The dividing line is set by the Tolman-Oppenheimer-Volkoff limit, approximately 2 to 3 solar masses, above which not even neutron degeneracy pressure can prevent continued gravitational collapse. The star's core, compressed beyond the density of an atomic nucleus, disappears behind an event horizon. Stellar mass black holes typically range from about 5 to perhaps 100 solar masses, though the upper end of this range has been pushed higher by recent gravitational wave observations. At the opposite extreme are supermassive black holes, monsters containing millions to billions of solar masses lurking at the centers of most large galaxies. The supermassive black hole at the center of our own Milky Way, Sagittarius AI, contains approximately 4 million solar masses, yet remains relatively quiescent, accreting only a trickle of material. Other supermassive black holes are far more active. When a supermassive black hole is actively feeding, accreting significant amounts of gas and dust, it produces what astronomers call an active galactic nucleus, or AGN. The most luminous AGN, historically called quasars, can outshine their entire host galaxies by factors of hundreds, radiating with luminosities of 10 to the 40 watts or more. The most massive known supermassive black holes exceed 10 billion solar masses. Some studies suggest the black hole at the center of the galaxy Phoenix A may approach 100 billion solar masses, though such extreme estimates remain uncertain. Between stellar mass and supermassive black holes lies a puzzling gap. The intermediate mass black holes, theorized to contain between roughly 100 and 100,000 solar masses. For many years, this class remained hypothetical, detected indirectly through the behavior of stars and gas in globular clusters or through X-ray observations of particularly luminous sources, but never confirmed with certainty. The situation changed dramatically in September 2020 with the announcement of gravitational wave event GW1990521. This remarkable detection recorded the merger of two black holes with masses of approximately 85 and 65 solar masses, producing a final black hole of 142 solar masses. This was the first definitive observation of a black hole in the intermediate mass range. It was also scientifically puzzling, because the heavier of the two progenitor black holes, 85 solar masses, falls within what astrophysicists call the pair instability mass gap. Stars massive enough to leave black holes in this range are expected to undergo pair instability supernovae, explosions so violent that they completely destroy the star and leave no remnant behind. The existence of an 85 solar mass black hole suggests either that our understanding of stellar evolution is incomplete, or that these black holes formed through some other mechanism, perhaps hierarchical mergers of smaller black holes in dense stellar environments like globular clusters. The formation of supermassive black holes presents an even deeper mystery. How do you build an object containing 1 billion solar masses? The straightforward answer, start with a stellar mass black hole and let it grow by accreting material, runs into severe difficulties. The rate at which a black hole can accrete is limited by radiation pressure. As infalling material heats up and radiates, the outward pressure of that radiation tends to push additional material away. This Eddington limit caps how fast a black hole can grow. Even at maximum accretion rate, building 1 billion solar mass black hole from a stellar mass seed would take longer than the age of the universe. Yet we observe quasars powered by such massive black holes when the universe was less than 1 billion years old, just a fraction of its current age. The seeds had to be more massive to begin with, or the accretion had to proceed faster than standard models allow. Several theories attempt to explain the rapid growth of supermassive black holes. Perhaps the first black holes formed from the direct collapse of massive primordial gas clouds, skipping the stellar phase entirely and producing seeds of 10,000 to 100,000 solar masses from the start. Perhaps early black holes experienced super Eddington accretion, feeding faster than the standard limit under special conditions. Perhaps multiple black holes merged hierarchically in the dense environments of early galaxies. Perhaps some exotic mechanism we haven't yet imagined played a role. The origin of supermassive black holes remains one of the outstanding problems in astrophysics. What we do know with certainty is that black holes, once formed, can experience catastrophic encounters with their surroundings. Among the most spectacular are tidal disruption events, which occur when a star wanders too close to a supermassive black hole and is torn apart by gravitational forces. The phenomenon works like this. Gravity is not uniform. An object as large as a star experiences stronger gravitational pull on the side nearest the black hole than on the side farthest away. This differential force, the tidal force, stretches the star. If the star approaches close enough, within the so-called tidal radius, the tidal forces exceed the star's own self-gravity, and the star is ripped apart. The stellar material forms an elongated stream, some of which falls into the black hole, while the rest is ejected into space. The process is sometimes called spaghettification, a wonderfully evocative term coined to describe how an object falling into a black hole would be stretched lengthwise and compressed sideways, like pasta being drawn through a pasta maker. For a stellar mass object falling into a stellar mass black hole, spaghettification occurs only very close to the event horizon. You'd be dead from radiation and gravitational effects long before tidal forces became significant. But for a star approaching a supermassive black hole, the tidal radius can lie well outside the event horizon, allowing the disruption to be observed before the material disappears. When a star is tidally disrupted, about half of its mass becomes gravitationally bound to the black hole and eventually accretes. The other half is ejected in unbound streams. The bound material forms an accretion disk that heats to millions of degrees, producing a brilliant flare of radiation across the electromagnetic spectrum. These tidal disruption events, or TDEs, can cause a normally quiescent supermassive black hole to suddenly blaze with luminosity rivaling a supernova, then gradually fade over months to years as the stellar debris is consumed. One of the best-studied tidal disruption events occurred in October 2019. Designated AT2019QIS, it was detected in a spiral galaxy approximately 215 million light-years from Earth in the constellation Eridanus, making it the closest tidal disruption event ever recorded. Astronomers observed the event from its earliest stages, watching as material was ejected at velocities up to 10,000 kilometers per second. Spectroscopic observations revealed the chemical composition of the disrupted star's atmosphere as it was being shredded. The data provided unprecedented detail about the physics of stellar destruction by black holes. Tidal disruption events occur perhaps once every 10 to 100,000 years per galaxy. Rare enough that observing one requires monitoring many galaxies simultaneously, but common enough that modern transient surveys now detect several dozen per year across the universe. Each detection offers a unique laboratory for studying supermassive black holes and the extreme physics of accretion. Even more violent than tidal disruption events are black hole mergers, which occur when two black holes inspiral and combine into a single larger black hole. Black hole binaries can form through several channels. Two massive stars born as a binary pair might both undergo supernova explosions, leaving behind a pair of black holes that remain gravitationally bound. Alternatively, black holes might capture each other dynamically in dense stellar environments, like globular clusters or the crowded centers of galaxies. In some cases, supermassive black hole binaries might form when galaxies merge, bringing their central black holes together over millions of years. The final merger of two black holes is an event of almost incomprehensible violence. In the last fraction of a second before the two event horizons combine, the black holes orbit each other at a significant fraction of the speed of light. The gravitational waves produced in this final stage are so powerful that they carry away a substantial fraction of the system's total mass energy, typically several percent. For a binary black hole merger, this can mean several solar masses worth of pure energy radiated away as gravitational waves in a fraction of a second. The peak luminosity of such an event, measured in energy radiated per second, exceeds the combined light of all the stars in the observable universe. The first direct detection of gravitational waves from a black hole merger occurred on September 14, 2015, when LIGO observed GW-14, the inspiral and merger of two black holes, approximately 36 and 29 solar masses, producing a final black hole of 62 solar masses. The roughly 3 solar masses of difference were radiated away as gravitational waves. This detection marked the first direct evidence that black holes could form binary systems, inspiral, and merge within the age of the universe. Since that inaugural detection, LIGO and Virgo have observed dozens of black hole mergers, revealing a population of stellar mass black holes with masses ranging from a few solar masses to over 80 solar masses. Some of these detections have raised profound questions. GW-190814, detected in August 2019, involved the merger of a 23 solar mass black hole with a 2.6 solar mass compact object, either the heaviest known neutron star or the lightest known black hole, straddling the uncertain boundary between these two classes of objects. GW-1905-1, as mentioned earlier, produced the first intermediate mass black hole ever observed. When two supermassive black holes merge, the gravitational waves are too low in frequency for Earth-based detectors to measure. These events, expected when galaxies merge and their central black holes eventually combine, will be targets for space-based gravitational wave observatories like the Laser Interferometer Space Antenna, LISA, planned for launch in the 2030s. Simulations suggest that the final stages of a supermassive black hole merger would produce gravitational waves detectable across the observable universe, announcing the formation of a new cosmic giant. The environments around supermassive black holes also produce dramatic phenomena through less cataclysmic means. Active galactic nuclei, black holes actively accreting significant amounts of material, generate some of the most energetic and persistent radiation in the universe. The accretion disk surrounding an active supermassive black hole can extend for light years and glow with luminosities exceeding 10 to the 40 watts. Material near the inner edge of the disk moves at nearly the speed of light and reaches temperatures of millions of degrees. In many cases, active galactic nuclei also produce powerful jets, beams of relativistic plasma launched perpendicular to the accretion disk, extending for thousands or even millions of light years into intergalactic space. The mechanism for jet formation is not completely understood, but likely involves the winding up of magnetic field lines by the rotating spacetime around the spinning black hole, a process described by the Blandford-Znajek mechanism. These jets carry enormous amounts of energy and can dramatically affect the evolution of their host galaxies, heating surrounding gas and suppressing star formation. When a jet points almost directly at Earth, we observe a blazar, an extremely luminous and highly variable source that can flicker dramatically on timescales of days or even hours. Blazars are among the most extreme objects known, occasionally flaring to luminosities that briefly make them the brightest persistent sources in the observable universe. The variability arises from the relativistic beaming of jet emission. Small changes in the jet's direction or intensity are amplified enormously in our frame of reference. Black holes also reveal themselves through their gravitational effects on nearby matter. Stars orbiting close to Sagittarius A, the Milky Way's central supermassive black hole, have been tracked for decades by teams led by Reinhard Genzel and Andrea Ghez, who shared the 2020 Nobel Prize in Physics for this work. The star S2, for instance, completes an orbit around the black hole in just 16 years, swooping within 17 light hours of the event horizon at speeds exceeding 7,000 kilometers per second, more than 2% of the speed of light. These observations provided the most precise measurement of the black hole's mass and confirmed the predictions of general relativity in extreme gravitational fields. In April 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow, the dark silhouette of the supermassive black hole at the center of the galaxy M87, some 55 million light-years away. The black hole contains approximately 6.5 billion solar masses, and its shadow appears as a dark region surrounded by a bright ring of hot, glowing gas. This historic image confirmed that the central objects in galaxies are indeed black holes, with event horizons consistent with general relativistic predictions. In May 2022, the collaboration released a similar image of Sagittarius A, our own galactic center black hole, completing the picture of these extraordinary objects. Black holes represent the ultimate gravitational catastrophe, the final collapse of matter into a state from which no escape is possible. They devour stars, warp spacetime, and eventually merge in explosions of gravitational energy that dwarf everything else in the cosmos. Yet they are also builders, not just destroyers. The energy released by accreting black holes heats gas in galaxies, regulating star formation and shaping galactic evolution. The jets from active nuclei distribute energy across intergalactic distances. The mergers of black holes send ripples through spacetime that carry information about the most extreme conditions in the universe. In black holes, we find both an ending and a continuing story, objects born from stellar death that go on to participate in cosmic processes far beyond their origins. They are nature's most extreme laboratories, regions where the physics that governs ordinary matter breaks down entirely and new rules apply. And with each new detection, each tidal disruption event, each gravitational wave merger, each blazar flare, we learn a little more about these most mysterious of cosmic objects. Imagine a magnetic field so powerful that it would rip the electrons from your atoms while you were still 500,000 kilometers away. A field so intense that it warps the very vacuum of space, causing normally invisible quantum effects to become physically significant. It is a field that could erase every credit card on Earth from a distance equal to half the moon's orbit. Such magnetic fields exist, and they are found in one of the strangest objects in the cosmic zoo, the magnetar. A magnetar is a type of neutron star, the collapsed city-sized remnant of a massive star that has exploded as a supernova. But while ordinary neutron stars possess magnetic fields millions of times stronger than Earth's, magnetars take this to an entirely different level. Their magnetic fields can exceed 10 to the 15 Gauss. That's a quadrillion times the strength of Earth's magnetic field and about 1,000 times stronger than a typical neutron star. These are the most powerfully magnetized objects known to exist anywhere in the universe. The existence of magnetars was first proposed in 1992 by Robert Duncan and Christopher Thompson, who were attempting to explain the peculiar behavior of objects called soft gamma repeaters, or SGRs. These sources would occasionally emit bursts of gamma rays, not the cosmological gamma ray bursts we discussed earlier, but shorter, less energetic bursts that appeared to repeat from the same location. Traditional neutron star models couldn't easily explain the energy source for these outbursts. Duncan and Thompson proposed that the decay of ultra-powerful magnetic fields could provide the necessary energy, and the magnetar hypothesis was born. As of 2025, approximately 30 magnetars have been identified, with several additional candidates awaiting confirmation. This small number reflects both the rarity of magnetars and the difficulty of detecting them. Unlike ordinary pulsars, which emit steady beams of radio waves, magnetars are often X-ray sources, requiring space-based observatories to study. They are also transient. Magnetar activity tends to occur in bursts, with long periods of relative quiescence between outbursts. The most dramatic demonstration of magnetar power occurred on December 27, 2004, when a magnetar designated SGR 18O-20 unleashed what remains the brightest explosion ever observed from any source in our galaxy beyond the Sun. This object lies approximately 50,000 light-years from Earth, about halfway across the Milky Way, on the far side of the galactic center. Despite this tremendous distance, the gamma-ray flare was so intense that it had measurable effects here on Earth. The initial spike of the giant flare lasted only about 0.2 of a second, but in that brief moment, SGR 1806 and 20 released as much energy as the Sun emits in 250,000 years. The gamma-ray flux was so extreme that it saturated virtually every space-based detector pointed anywhere near its direction. NASA's SWIFT satellite, designed to detect gamma-ray bursts, was completely overwhelmed even though it wasn't pointed at the source. The radiation punched through the walls of the spacecraft. The burst was bright enough that several satellites detected it reflected off the moon. Here on Earth, 50,000 light-years from the explosion, the gamma rays ionized the upper atmosphere, temporarily expanding the ionosphere and affecting radio wave propagation. Some fishermen in the Arctic reportedly saw an unusual aurora at the moment of the flare. The energy release was approximately 10 to the 46 ergs, roughly 100 times more powerful than the two previous giant flares ever recorded from magnetars. This was, as astronomers sometimes put it, a once-in-a-lifetime event for both the observers and, quite possibly, for the magnetar itself. What caused this colossal explosion? The leading theory points to a phenomenon called a starquake, a fracture in the magnetar's solid crust. Unlike ordinary neutron stars, whose magnetic fields are relatively stable, magnetars are constantly stressed by their own magnetism. The ultra-powerful field threads through the neutron star's crust and is anchored in the deep interior, where superdense nuclear matter constrains its evolution. Over time, magnetic stresses build up in the crust, deforming it until something breaks. When a magnetar's crust fractures, the results are catastrophic. The magnetic field, suddenly freed from the constraints of the old crustal configuration, snaps and reconnects in a process analogous to solar flares, but vastly more powerful. The energy stored in the twisted magnetic field is released in a flash of gamma rays and X-rays. The crust may shift by only a centimeter, But given the incredible density of neutron star material, that tiny displacement releases energy equivalent to many megatons of TNT. The analogy to earthquakes is more than rhetorical. In the aftermath of the December 2004 flare, researchers analyzing data from NASA's Rossi X-ray Timing Explorer detected oscillations in the X-ray emission from SGR 1806-1020. These oscillations, occurring at a frequency of 94.5 Hz, persisted for several minutes after the initial blast and are interpreted as the ringing of the magnetar, seismic vibrations propagating through the neutron star's crust and interior. As one researcher poetically noted, this frequency is close to the 22nd key of a piano, F sharp. The magnetar was literally humming after its starquake. These quasi-periodic oscillations provide a unique window into the internal structure of neutron stars, one of the most challenging problems in astrophysics. We cannot directly probe the interior of a neutron star. The conditions there exceed anything achievable in terrestrial laboratories. But by observing how magnetars ring after starquakes, we can infer properties of the crust and core, much as seismologists use earthquake waves to study Earth's interior. Different oscillation frequencies correspond to different vibrational modes, each sensitive to particular aspects of the neutron star's structure and composition. The magnetic fields of magnetars are not only extraordinarily strong, but also extraordinarily dynamic. Unlike stable magnetic fields that persist for billions of years, magnetar fields decay on timescales of approximately 10,000 years. This decay is what powers most of the magnetar's observed emission. As the magnetic field dissipates, the energy must go somewhere, into heating the crust, into bursts of radiation, into accelerating particles. Once the field has decayed to more typical neutron star levels, the magnetar effectively switches off, becoming an ordinary dim cooling neutron star. Given this short active lifetime, the fact that we observe approximately 30 active magnetars today suggests that many more, perhaps 30 million or more, have already gone quiet and lurk undetected throughout the galaxy. Magnetars produce several distinct types of outbursts. The most common are short bursts lasting fractions of a second, which release 10 to the 36 to 10 to the 41 ergs and occur sporadically during periods of activity. More rarely, magnetars produce intermediate flares with energies around 10 to the 43 ergs. The giant flares like the December 2004 event are extremely rare. Only 3 have been observed in over 50 years of monitoring. One from SGR 052566 in 1979, one from SGR 1900+14 in 1998, and the 2004 event from SGR 1806-20. Each giant flare was more energetic than the last, though this may reflect selection effects in detection rather than an actual trend. Intriguingly, magnetars have recently been connected to another mysterious phenomenon, fast radio bursts, or FRBs. These are brief pulses of radio waves lasting only milliseconds that appear to originate from extragalactic distances. First discovered in 2007, fast radio bursts remained unexplained for over a decade. Their brevity suggested a compact source, perhaps related to neutron stars, but the extreme energies required for detectability across cosmological distances ruled out ordinary pulsar emission. In April 2020, a breakthrough occurred when the CHIME and STARE-2 radio telescopes detected an extremely bright radio burst from SGR 1935-PLO-215Fu, a known magnetar in our own galaxy. The burst was accompanied by X-ray emission detected by several satellites, confirming that magnetars can produce fast radio burst-like emissions. While this galactic burst was far less luminous than the extragalactic fast radio bursts, it established a clear connection between magnetars and at least some FRBs. The extreme magnetic fields may generate coherent radio emission during flares, potentially explaining one of the most puzzling phenomena in radio astronomy. Magnetars are not the only exotic stellar remnants capable of spectacular outbursts. Anomalous X-ray pulsars, or AXPs, represent a related class of objects that share many properties with magnetars. In fact, the distinction between magnetars and AXPs has largely dissolved as observations have revealed that both categories represent neutron stars powered by magnetic field decay rather than rotation. The McGill SGR AXP online catalog now lists both types together as confirmed and candidate magnetars. Beyond magnetars, the universe contains other categories of extreme stellar objects capable of producing violent phenomena. X-ray binaries, systems in which a neutron star or black hole accretes material from a companion star, can produce dramatic outbursts when instabilities in the accretion disk cause sudden increases in mass transfer. Some X-ray binaries launch relativistic jets that produce radio emission and can occasionally rival gamma-ray bursts in certain respects. The microquasar GRS 1915+105, for instance, has been observed to launch blobs of plasma at apparent speeds exceeding the speed of light, an optical illusion caused by material moving at 92% of light speed at an angle to our line of sight. Millisecond pulsars represent another category of extreme neutron star. These are old pulsars that have been spun up by accreting material from a binary companion, reaching rotation rates as high as 7 to 16 revolutions per second. At such speeds, the surface of the neutron star moves at roughly 25% of the speed of light, and the centrifugal forces approach the limits of what the star can sustain before tearing itself apart. While millisecond pulsars are remarkably stable, they serve as some of the best clocks in the universe. Occasional glitches in their rotation reveal sudden adjustments in their internal structure. The existence of magnetars and other stellar exotica reminds us that neutron stars are not simply compressed balls of neutrons, but complex objects with internal structure, dynamics, and evolution. Their cores may contain exotic phases of matter, perhaps quark matter, where the quarks that normally make up protons and neutrons are liberated from confinement. Perhaps strange matter, containing strange quarks in addition to the up and down quarks of ordinary matter. Perhaps other phases that remain theoretical because they cannot be produced in any terrestrial laboratory. Each magnetar outburst, each pulsar glitch, each oscillation detected in the aftermath of a starquake provides clues about the nature of matter under conditions billions of times denser than anything found on Earth. The extreme magnetism of magnetars also has implications for fundamental physics. In such powerful magnetic fields, the vacuum itself behaves differently. According to quantum electrodynamics, the vacuum is not truly empty, but filled with virtual particle-antiparticle pairs that continuously appear and disappear. In a sufficiently strong magnetic field, these virtual pairs can become polarized, causing the vacuum to behave like a birefringent crystal, splitting light into different polarization components that travel at different speeds. This effect, called vacuum birefringence, was predicted decades ago but is extraordinarily difficult to detect. Observations of magnetars offer one of the best prospects for confirming this exotic quantum effect, and tentative evidence has been reported from polarization measurements of magnetar X-ray emission. If a magnetar were located within about 10 light-years of Earth, a giant flare like the December 2004 event could cause significant damage to our atmosphere. The gamma rays would ionize nitrogen and oxygen, producing nitrogen oxides that would deplete the ozone layer. The resulting increase in ultraviolet radiation at the surface could damage ecosystems and potentially trigger a mass extinction. Fortunately, no known magnetar is anywhere near this close. The nearest identified magnetar, 1E 1048.1.5937, lies approximately 9,000 light-years away in the constellation Carina. We appear to be safe from magnetar-induced catastrophe, though given that many magnetars have gone dormant and are no longer detectable, we cannot be entirely certain of what lurks in our cosmic neighborhood. The study of magnetars reveals nature operating at extremes far beyond ordinary experience. Their magnetic fields dwarf anything achievable in human technology by factors of trillions. Their densities exceed that of atomic nuclei. Their starquakes release more energy in a fraction of a second than the sun emits in millennia. And yet, these exotic objects are simply the natural outcomes of stellar evolution. the remnants of massive stars that happen to possess the right combination of mass, rotation, and magnetic field to become magnetars rather than ordinary pulsars. In the catalog of cosmic catastrophes, magnetar flares occupy a unique niche. They are not the most powerful events. Supernova and gamma-ray bursts release far more total energy, but they are among the most concentrated, releasing stupendous amounts of energy in tiny fractions of a second from objects smaller than a city. They represent the universe, showing us what happens when matter and magnetism are pushed to their utmost limits. And they remind us that even familiar categories of objects, neutron stars have been studied for over half a century, can still surprise us with previously unimagined behaviors. The December 2004 flare from SGR 180620 may have been a once-in-a-lifetime event, but somewhere in the galaxy, another magnetar's crust is building stress, accumulating strain energy in its twisted magnetic field. Someday, perhaps tomorrow, perhaps in 1,000 years, that crust will crack and another giant flare will illuminate the cosmos. Scientists around the world will scramble to observe it with every available instrument, gathering data that will help unlock the remaining mysteries of these extraordinary objects. The universe, it seems, is never short of ways to astonish us. We've journeyed to the far corners of the cosmos, exploring the cataclysmic deaths of massive stars, the collisions of neutron stars, and the impossible magnetism of magnetars. But now, let's turn our attention closer to home. Much closer. Let's talk about the star that rises each morning, the yellow dwarf we call the Sun. Because while our Sun may seem benign compared to the cosmic monsters we've discussed, make no mistake, it is capable of violence that could fundamentally disrupt our technological civilization. On the morning of September 1st, 1859, the English astronomer Richard Carrington was in his private observatory, sketching a particularly large cluster of sunspots, when something extraordinary happened. A sudden flash of white light erupted from the sunspot region, so brilliant, so unexpected, that Carrington initially thought his equipment had malfunctioned. He wasn't alone in his observation. Another astronomer, Richard Hodgson, working independently in London, witnessed the same phenomenon. Within minutes, the intensity faded, but the two men had just become the first humans in recorded history to observe a solar flare. What Carrington and Hodgson could not have known was that the flash of light was merely the visible signature of something far more dangerous hurtling toward Earth. A massive coronal mass ejection, a billion-ton cloud of magnetized plasma, had been launched from the Sun's surface and was racing through space at extraordinary speed. Where typical coronal mass ejections take 3 to 4 days to reach Earth, this one arrived in just 17.6 hours. Scientists now believe its exceptional velocity resulted from a prior eruption that had cleared the ambient solar wind from its path, allowing the second, more powerful ejection to travel essentially unimpeded. When the coronal mass ejection struck Earth's magnetic field on September 2, 1859, the effects were immediate and spectacular. Auroras, normally confined to polar latitudes, erupted across the globe. The northern lights were visible as far south as Cuba, Hawaii, and even Colombia. In the Rocky Mountains of North America, the auroral glow was so bright that gold miners reportedly awoke and began preparing breakfast, thinking dawn had arrived. In the northeastern United States, people could read newspapers by the light of the aurora alone, but the beauty masked a more sinister effect. The geomagnetic storm induced powerful electrical currents in the ground, a phenomenon we now call geomagnetically induced currents. These currents found their way into the global telegraph network, the most advanced technology of the era. Telegraph systems across Europe and North America failed catastrophically. Operators reported receiving electric shocks from their equipment. Telegraph paper caught fire from the sparks. In some offices, the induced currents were so strong that operators disconnected their batteries entirely and found they could continue sending messages using the celestial power alone. An astonishing exchange was recorded between telegraph operators in Boston and Portland on the night of September 2, 1859. After disconnecting their power sources, the Boston operator asked, Please cut off your battery entirely for 15 minutes. Portland complied, and Boston then asked, "Mine is disconnected, and we are working with the auroral current. How do you receive my writing?" Portland's response, "Better than with our batteries on." This event, now called the Carrington event, was the most intense geomagnetic storm in recorded history. The Disturbance Storm Time Index, or DIEST, a measure of geomagnetic intensity, has been estimated at -850 to -900 nanoteslas for this event, making it roughly twice as intense as the most powerful storms of the 20th century. The solar flare that triggered it has been retrospectively classified as approximately X45, one of the most powerful solar explosions ever documented, though ever documented only extends back about 200 years of reliable records, a mere eye blink in cosmic time. In 1859, the telegraph was the height of technology. What would a Carrington-class event do to our modern world? The answer is sobering. Our civilization runs on electricity, and that electricity flows through an interconnected web of transformers, transmission lines, and power stations that are exquisitely vulnerable to geomagnetically induced currents. High-voltage transformers, the critical nodes of our power grid, can be damaged or destroyed by the quasi-direct currents induced during severe geomagnetic storms. These transformers are custom-built, enormously expensive, and require months or even years to manufacture and install. A sufficiently severe storm could knock out transformers across entire continents, leaving hundreds of millions without power for extended periods. We received a warning shot on March 13, 1989, when a severe geomagnetic storm struck Earth. The culprit was a coronal mass ejection launched by an X-15-class solar flare from a particularly active sunspot region. When the storm arrived, its effects cascaded through the power infrastructure. Just 90 seconds after the disturbance began, the entire Hydro-Quebec power grid collapsed. 6 million people lost electricity for 9 hours. The province was plunged into darkness on a cold March night. Schools and businesses closed. The Montreal Metro shut down during morning rush hour, and the Dorval Airport ceased operations. The Quebec blackout occurred because the province sits on the Canadian Shield, a vast region of ancient rock that is a poor electrical conductor. Geomagnetically induced currents could not easily dissipate into the ground, so they flowed instead through the path of least resistance, the high-voltage transmission lines of the power grid. Circuit breakers tripped in rapid succession. Transformers experienced dangerous harmonics. The cascade of failures was so swift that operators had virtually no time to respond. Across the border in the United States, more than 200 grid faults occurred within minutes of the storm's onset. Operators managed to root around the problems and avoid major blackouts, but just barely. Later analysis revealed that the U.S. power grid had come far closer to widespread collapse than anyone realized at the time. Meanwhile, in space, the storm wreaked havoc on satellites. NASA's TDRS-1 communication satellite recorded over 250 anomalies from high-energy particles penetrating its electronics. The Space Shuttle Discovery, launched the same day, experienced a mysterious sensor malfunction that resolved only after the storm subsided. The March 1989 event was significant, but it was not a Carrington-class storm. Studies of geomagnetic intensity suggest the Carrington event was roughly 2 to 3 times more powerful. A 2013 study by the insurance company Lloyd's of London estimated that a Carrington-class event today could affect 20 to 40 million Americans, with power outages lasting weeks to months in some regions. The economic cost was estimated at $1 to $2 trillion, and some analyses suggest even this staggering figure may be conservative. In July 2012, The Sun reminded us that such events are not merely historical curiosities. A massive coronal mass ejection, comparable in scale to the Carrington event, erupted from the Sun and raced through the inner solar system. Fortunately, it missed Earth entirely, passing through our orbital path about 9 days before we arrived at that point. Had the eruption occurred just 1 week earlier, we would have experienced a direct hit. As physicist Daniel Baker of the University of Colorado stated, "If it had hit, we would still be picking up the pieces." And now, we come to a more unsettling revelation. In December 2024, researchers from the Max Planck Institute for Solar System Research published findings suggesting that our sun may be capable of producing events far more powerful than the Carrington event, events called superflares. By analyzing data from NASA's Kepler Space Telescope, which monitored 56,050 sun-like stars for roughly 4 years, the team identified 2,189 superflares erupting from 2,127 of these stars. These superflares released energies ranging from 10 to the 34 to 10 to the 36 ergs, roughly 10 to 10,000 times more powerful than the strongest solar flares ever recorded from our own sun. The striking conclusion: sun-like stars appear to produce superflares approximately once per century. This rate is 40 to 50 times more frequent than previous estimates had suggested. The researchers noted that the pattern of flare occurrence on these sun-like stars matches the statistical pattern of our own sun's flares when extrapolated to higher energies, suggesting both are generated by the same physical mechanism. If our sun behaves like its stellar siblings, it could produce a superflare at any time, though any time in astronomical terms could mean tomorrow or could mean centuries from now. The Carrington event released perhaps 10 to the 32 ergs, already catastrophic for a civilization dependent on electricity. A superflare at the lower end of the observed range would release 100 times more energy. The potential consequences for Earth are difficult to fully comprehend, though some researchers have speculated about mass destruction of the ozone layer, significant increases in surface radiation, and disruptions to ecosystems alongside the complete collapse of technological infrastructure. Evidence of past extreme solar events can be found in an unlikely archive: tree rings. Researchers have discovered spikes in carbon-14 concentrations produced when cosmic radiation strikes atmospheric nitrogen in tree rings dating to specific years in the distant past. A particularly significant spike has been identified around 774-775 CE, now called the Milky Way event, which appears to represent a solar particle event roughly 50 times more intense than any observed in the modern era. Similar events have been identified in tree ring and ice core records dating to approximately 7176 BCE and 5259 BCE. These ancient solar storms occurred during periods when human civilization depended on stone tools and candlelight rather than transistors and transformers. Today, such events would be civilizational threats. But here's the curious thing: for all their potential danger, solar flares and coronal mass ejections are fundamentally ordinary stellar behavior. Our sun is not a particularly violent star. Compared to younger, more magnetically active stars, it is actually quite sedate. The mechanisms that produce solar flares, magnetic field lines twisting, tangling, and suddenly reconnecting to release stored energy, are the same mechanisms that produce flares on stars throughout the galaxy. We simply happen to live close enough to one particular star that its tantrums matter very much to us. The European Space Agency is preparing to launch a mission called Vigil in 2031 that will monitor the Sun from a position at the L5 Lagrange point, a gravitationally stable location trailing Earth in its orbit. From there, Vigil will be able to observe the Sun's surface about 4.5 days before active regions rotate to face Earth, providing crucial advance warning of potentially dangerous sunspots. NASA and NOAA already operate solar monitoring satellites, and the Space Weather Prediction Center issues forecasts and alerts when dangerous conditions develop. But forecasting is not the same as prevention. We cannot stop the sun from flaring any more than we can stop earthquakes. We can only prepare, and the preparedness of our power infrastructure remains a matter of debate. Some utilities have installed protective equipment, many have not. The Federal Energy Regulatory Commission has ordered utilities to develop standards for protecting against severe geomagnetic storms, but implementation varies widely. The sun rises each morning, and we take for granted that it will provide light and warmth without menace. But our star is a thermonuclear furnace 864,000 miles across, fusing 600 million tons of hydrogen into helium every second, generating temperatures of 15 million degrees in its core, and driving complex magnetic dynamics we still don't fully understand. It has been relatively quiet during the centuries of our technological development. It may not always be so quiet. And when it next unleashes a Carrington-class event, or something worse, we will discover whether our civilization has prepared adequately for the violence of our own star. Of all the cosmic catastrophes we've explored, there is one that feels distinctly personal. Supernovae occur at safe distances. Gamma-ray bursts happen in distant galaxies. Magnetar flares are confined to the far side of the Milky Way, but asteroids and comets are already here in our cosmic neighborhood, orbiting the Sun on paths that sometimes cross our own. They are the cosmic bullets that have struck Earth before, that will strike again, and that we are only beginning to learn how to dodge. 66 million years ago, on a day that changed the history of life on Earth, a roughly 10-kilometer-wide asteroid entered the atmosphere over what is now the Yucatan Peninsula of Mexico. It was traveling at approximately 20 kilometers per second, roughly 58 times the speed of sound, and struck the shallow ocean at an angle between 45 and 60 degrees. The energy released in that instant has been calculated at approximately 10 to the 23 joules, equivalent to 100 teratons of TNT. This was more than 1 billion times the energy of the atomic bombs dropped on Hiroshima and Nagasaki combined, more than 1 billion times. The asteroid itself, vaporized on impact, transformed almost instantaneously from solid rock to superheated plasma, but its momentum and energy were transferred to the target rocks with catastrophic efficiency. The impact excavated a crater roughly 200 kilometers in diameter and 30 kilometers deep. The displaced material, vaporized rock, molten droplets, and solid fragments, was blasted upward and outward at velocities exceeding 5 kilometers per second. Within hours, this ejecta had circled the globe, showering the entire planet with tiny spherules of melted rock. The immediate effects were almost unimaginable. Superheated winds, moving at over 1,000 kilometers per hour, radiated outward from the impact site for 900 to 1,800 kilometers, incinerating everything in their path. A fireball lit the sky, visible from thousands of miles away. Magnitude 11 earthquakes, more powerful than any earthquake in recorded human history, rippled through the Earth's crust. Tsunamis perhaps 1,000 feet high raced across the Gulf of Mexico. At a site called Tanis in North Dakota, over 3 kilometers from the impact, researchers have found evidence of fish killed within minutes of the collision, their gills choked with impact debris, their bodies buried by seismic-induced waves. But the immediate destruction was only the beginning. The longer-term effects proved even more deadly. Vast quantities of sulfur-containing rock had been vaporized, injecting sulfate aerosols into the atmosphere that blocked sunlight and triggered rapid global cooling. Dust and soot from worldwide fires further darkened the skies. Photosynthesis collapsed. In the oceans, plankton died en masse, breaking the foundation of marine food chains. On land, plants withered, and the herbivores that depended on them starved, followed by the carnivores that preyed on the herbivores. Within a geological instant, perhaps just thousands of years, approximately 75% of all species on Earth were extinct. The non-avian dinosaurs, which had dominated terrestrial ecosystems for over 160 million years, vanished entirely. So did the flying pterosaurs and the marine reptiles. The ammonites, spiral-shelled relatives of the modern nautilus that had thrived in Earth's oceans for hundreds of millions of years, disappeared. It was the 5th mass extinction in Earth's history, and it was caused by a rock from space. The evidence for this impact was not discovered until 1980, when a team led by physicist Luis Alvarez and his geologist son Walter identified an anomalous concentration of the element iridium in a thin clay layer marking the Cretaceous-Paleogene boundary, the geological division between the age of dinosaurs and the age of mammals. Iridium is rare in Earth's crust, but common in asteroids. The Alvarez team proposed that an asteroid impact had distributed this iridium globally. The hypothesis was controversial at first, but in 1991, researchers identified the smoking gun, the Chicxulub crater, buried beneath hundreds of meters of sediment in Mexico's Yucatan Peninsula. Subsequent dating confirmed the crater formed precisely 66 million years ago at the moment of the mass extinction. In August 2024, researchers published findings identifying the specific type of asteroid responsible. By analyzing ruthenium isotopes, another element rare on Earth but common in space rocks, in 66 million-year-old sediments from Denmark, Italy, and Spain, scientists determined that the Chicxulub impactor was a carbonaceous chondrite asteroid, a type rich in carbon compounds and water that typically forms in the outer solar system beyond Jupiter's orbit. These C-type asteroids, as they're called, are among the most primitive objects in the solar system, and the confirmation adds to our understanding of the threat they pose. The Chicxulub impact was, by any measure, a worst-case scenario, or nearly so. But Earth has been struck many times by objects of various sizes and will be struck again. The question is not if, but when and whether we will be prepared. On June 30, 1908, a far smaller but still dramatic impact occurred in one of the most remote regions on Earth. At approximately 7:14 in the morning local time, an asteroid roughly 50 to 60 meters in diameter entered the atmosphere over the sparsely populated Siberian taiga near the Podkamenaya Tunguska River. Traveling at perhaps 27 kilometers per second, the object heated to incandescence as it plunged through the thickening air, experiencing pressures that exceeded its structural strength. At an altitude of 5 to 10 kilometers, it explosively disintegrated. The airburst released energy estimated at 3 to 15 megatons of TNT, roughly 1,000 times the power of the Hiroshima bomb, and comparable to a modern hydrogen bomb. The shockwave flattened 80 million trees across more than 2,000 square kilometers of forest. Eyewitnesses up to 65 kilometers away reported being thrown to the ground by the blast. The heat was so intense that a man sitting on his porch over 40 miles from the epicenter reported that his shirt felt like it was on fire. Seismographs registered the disturbance across Europe. The atmospheric shock wave circled the globe twice. Remarkably, because of the region's extreme isolation, no confirmed human deaths occurred, though reindeer herds were decimated, and a few unverified reports suggest some indigenous people may have perished. The Tunguska event left no impact crater because the object never reached the ground intact. It disintegrated in the atmosphere, converting its kinetic energy into blast and heat. But had it detonated over a city, London, Paris, Moscow, the casualties would have numbered in the millions. The Tunguska object was small by cosmic standards, perhaps the size of a large building. There are millions of such objects in the inner solar system, and we have cataloged only a fraction of them. On February 15, 2013, we received another reminder of this threat. A roughly 20-meter asteroid entered the atmosphere over Chelyabinsk, Russia, and exploded at an altitude of about 30 kilometers. The airburst released approximately 500 kilotons of energy, about 30 times the Hiroshima bomb. The flash was brighter than the sun, visible from hundreds of kilometers away. The shockwave blew out windows across the city, sending glass shards flying into buildings where people had gathered to watch the fireball. Over 1,600 people were injured, most from flying glass. The explosion was captured on countless dashcam and security cameras, providing the first extensive documentation of a significant impact event. The Chelyabinsk meteor arrived from the direction of the sun, making it effectively invisible to our ground-based telescopes until it struck. We had no warning whatsoever. The object had simply evaded detection, lurking in the sun's glare until it was upon us. These events illuminate a sobering reality. Earth orbits through a cosmic shooting gallery. NASA's Center for Near-Earth Object Studies tracks more than 35,000 near-Earth asteroids, objects whose orbits bring them within 50 million kilometers of Earth's path. Of these, over 2,300 have been classified as potentially hazardous asteroids, meaning they are both large enough to cause regional damage, 140 meters or more, and have orbits that pass within 7.5 million kilometers of Earth. Larger objects, those capable of global catastrophe, are easier to find, and NASA has cataloged an estimated 95% of near-Earth asteroids 1 kilometer or larger in diameter. None of those currently known poses a significant threat within the next century, but smaller objects remain problematic. We have found perhaps 40% of near-Earth asteroids larger than 140 meters. For objects the size of the Tunguska impactor, 50 meters or so, we have cataloged only a tiny fraction. These objects are faint, numerous, and often discovered only when they pass close to Earth. The Chelyabinsk object was never detected at all until it arrived. The good news is that humanity is beginning to take this threat seriously, and we have demonstrated, for the first time in history, the technological capability to do something about it. On September 26, 2022, at 7:14 p.m. Eastern Time, NASA's Double Asteroid Redirection Test spacecraft, DART, deliberately collided with Dimorphos, a small moonlet orbiting the larger asteroid Didymos. Dimorphos was approximately 160 meters in diameter, roughly the size of asteroids that could devastate a region if they struck Earth. DART weighed only 570 kilograms, about the mass of a small car, but it struck at 6.6 kilometers per second. The impact worked. Before DART, Dimorphos orbited Didymos every 11 hours and 55 minutes. After the impact, that orbital period had shortened to 11 hours and 23 minutes, a change of 32 minutes. NASA had defined mission success as a change of at least 73 seconds. DART exceeded that threshold by more than 25 times. The collision also ejected an estimated 16 million kilograms of asteroidal debris, creating a comet-like tail visible to telescopes around the world. The recoil from this ejected material substantially enhanced DART's push against Dimorphos. This was proof of concept for kinetic impact deflection, using a spacecraft to nudge an asteroid onto a different trajectory. Given sufficient warning time, even a small change in velocity can accumulate over years or decades into a large change in position, turning a direct hit into a near miss. The European Space Agency's Hera mission, launched in 2024, will arrive at the Didymos system in late 2026 to conduct detailed follow-up observations, measuring Dimorphos's mass and imaging the crater DART left behind. Of course, kinetic impact is not the only option. For larger asteroids or shorter warning times, more dramatic measures might be needed. Nuclear devices, detonated near or on the surface of an asteroid, could provide far more impulse than any kinetic impactor. A standoff nuclear detonation, exploding the device at some distance from the asteroid's surface, would vaporize material on the near side, creating a jet of expanding gas that acts like a rocket engine. This approach could deflect even a large asteroid with sufficient warning. Other proposals include gravity tractors, spacecraft that hover near an asteroid, using their own gravity to slowly tug it off course, and ion beam deflection, using focused particle beams to ablate surface material. All of these methods share a common requirement: time. Deflection is most effective when begun years or decades before a potential impact. This is why detection and early warning remain paramount. NASA's Planetary Defense Coordination Office coordinates American efforts to find and track potentially hazardous objects. The upcoming NEO Surveyor mission, scheduled for launch in the coming years, will search for near-Earth asteroids from space using infrared sensors, capable of detecting even dark carbon-rich asteroids that reflect little visible light. The dinosaurs had no telescopes, they had no space program, they had no warning when their world ended. We have all of these things. The question is whether we will use them wisely. The asteroids are still out there, still orbiting, still occasionally crossing Earth's path. In the cosmic lottery of impact events, Earth has been relatively lucky during the brief span of human civilization. That luck will not last forever. But for the first time in the 4-5 billion year history of our planet, one species, us, has the knowledge to see the threat coming and the technology to potentially stop it. That is not a small thing. That may in fact be one of the most remarkable achievements of our species, the capacity to prevent our own extinction from the most ancient of cosmic hazards. But the capacity to prevent is not the same as guaranteed prevention. It requires vigilance, investment, international cooperation, and the wisdom to prepare for threats that may not arrive for centuries, or may arrive tomorrow. The cosmic bullets are still flying. Whether we survive them depends on us. The catastrophes we've examined so far unfold quickly by cosmic standards. Supernovae explode in seconds, asteroids strike in instants, even solar flares reach us in mere hours. But the universe also practices a grander, slower form of violence. Across hundreds of millions of years, entire galaxies collide, merge, and devour one another. Stars by the hundreds of billions are flung into new orbits. Supermassive black holes spiral together and eventually combine. The very shape of galactic structures is torn apart and reformed. This is cosmic cannibalism on the largest possible scale, and our own Milky Way may be next on the menu. Look up on a dark autumn night in the northern hemisphere, and you might spot a faint smudge of light in the constellation Andromeda. That smudge is the Andromeda Galaxy, also known as Messier 31, and it contains roughly 1 trillion stars spread across a disk some 220,000 light-years in diameter. It is the nearest major galaxy to our Milky Way, and it is heading directly toward us at approximately 110 kilometers per second, about 250,000 miles per hour. This motion was first detected over a century ago. In 1912, the astronomer Vesto Slipher measured the spectral lines of Andromeda and discovered they were blue-shifted, compressed toward shorter wavelengths, indicating the galaxy was approaching rather than receding. At the time, astronomers were unsure whether Andromeda was even a separate galaxy or merely a nebula within our own. That question was resolved in the 1920s when Edwin Hubble identified Cepheid variable stars in Andromeda and used them to measure its distance, conclusively proving it was a vast stellar system far beyond the Milky Way. For decades, the question of whether Andromeda would actually collide with the Milky Way remained open. We knew Andromeda was approaching in the radial direction along the line between us, but we couldn't accurately measure its sideways motion, what astronomers call proper motion. Without knowing whether Andromeda was drifting sideways as it approached, we couldn't determine if it would strike us head-on, deliver a glancing blow, or miss entirely. In 2012, astronomers using the Hubble Space Telescope finally measured Andromeda's proper motion with sufficient precision to answer the question. By tracking the positions of stars in Andromeda over the course of 7 years, they determined that the galaxy's sideways velocity was essentially consistent with zero. Andromeda and the Milky Way appeared to be on a collision course, with merger predicted in roughly 4 billion years. The announcement made headlines worldwide, but science progresses, and newer data has introduced substantial uncertainty. In June 2025, researchers led by Till Sawala of the University of Helsinki published a reanalysis incorporating the latest observations from both the Hubble Space Telescope and the European Space Agency's Gaia mission. Their findings were startling. When the gravitational influences of smaller satellite galaxies, particularly the Large Magellanic Cloud and the Triangulum Galaxy, are taken into account, the outcome becomes far less certain. The Large Magellanic Cloud, a satellite galaxy of the Milky Way containing perhaps 15% of our galaxy's mass, orbits in a plane roughly perpendicular to the Milky Way Andromeda trajectory. Its gravitational pull tugs our galaxy slightly off course. The Triangulum Galaxy, meanwhile, is a satellite of Andromeda that pulls our galaxy slightly toward Andromeda. When these competing influences are factored into computer simulations, run 100,000 times with varying initial conditions, the researchers found only a roughly 50% probability that the Milky Way and Andromeda will collide within the next 10 billion years. There is approximately a 2% chance of a head-on collision within 4 to 5 billion years, as previously predicted. In about half the simulations, the two galaxies experience close encounters, but continue orbiting each other for billions of years without merging. Whether or not the Milky Way and Andromeda ultimately merge, galaxy collisions are extremely common in the universe. The Hubble Space Telescope has captured dozens of spectacular images of colliding galaxies in various stages of interaction. The antennae galaxies, NGC 4038 and NGC 4039, show two spiral galaxies in the midst of a violent embrace, their spiral arms stretched into long tidal tails while intense star formation rages in the regions where their gas clouds collide. The mice galaxies display two galaxies connected by streaming bridges of stars. The Cartwheel galaxy bears the scars of a smaller galaxy that punched straight through its center, triggering a ring-shaped wave of star formation that continues expanding outward. When galaxies collide, stars rarely strike each other. This seems counterintuitive. Surely when a trillion stars meet a trillion stars, some must collide. But the distances between stars are so vast compared to their sizes that actual stellar collisions are extraordinarily rare. If the Sun were the size of a ping-pong ball, the nearest star, Proxima Centauri, would be another ping-pong ball about 2,100 kilometers away. The average distance between stars in the Milky Way is roughly 160 billion kilometers, or about 1,000 astronomical units. Even during a galactic merger, with two stellar populations passing through each other, the probability of any particular star suffering a direct collision is negligible. What does happen is more subtle, but still dramatic. The gravitational interactions between the two galaxies redistribute stars into entirely new orbits. The beautiful spiral arms of each galaxy are disrupted, stretched into tidal tails that can extend for hundreds of thousands of light years. Some stars are flung out of the merging system entirely, becoming intergalactic vagabonds wandering the cosmic void. The gravitational potential of the combined system eventually settles into a new configuration, typically an elliptical galaxy, a smooth, football-shaped collection of stars lacking the spiral structure that characterized the original galaxies. Gas clouds, unlike stars, can and do collide. When the interstellar medium of one galaxy encounters the interstellar medium of another, the result is spectacular compression that triggers intense bursts of star formation. The collision regions glow with the light of thousands of newborn stars, giving merging galaxies their characteristically chaotic, luminous appearance. In extreme cases, this merger-induced star formation can consume the available gas rapidly, leaving the resulting elliptical galaxy relatively sterile, unable to form new stars. At the centers of both the Milky Way and Andromeda lurk supermassive black holes. Our galaxy's central black hole, Sagittarius AI, contains approximately 4 million solar masses. Andromeda's central black hole is considerably more massive, estimated at 100 to 200 million solar masses. When the two galaxies merge, these black holes will eventually find each other, spiraling together through a process called dynamical friction as they transfer orbital energy to surrounding stars. The final coalescence may take hundreds of millions of years, but eventually the two black holes will merge, releasing a burst of gravitational waves and forming a single, more massive black hole at the center of the new combined galaxy. Computer simulations of the Milky Way-Andromeda merger, created by NASA and others, show a stately cosmic dance unfolding over billions of years. In about 2 billion years, Andromeda will appear noticeably larger in Earth's sky as the gap closes. In about 3.5 billion years, Andromeda will fill the night sky. Its disk stretching across the heavens in a display our distant descendants, if any exist, would find awe-inspiring. In about 385 billion years, the first close passage occurs, with tidal forces distorting both galaxies, triggering waves of star formation that light up the sky. Multiple subsequent passages follow, each stripping more stars from their original orbits, until finally, around 6 to 7 billion years from now, the two galaxies have merged into a single massive elliptical galaxy. Astronomers have nicknamed this future entity Milky Way. Should we worry about this impending merger? Not personally, no. Our sun will have long since exhausted its hydrogen fuel and swelled into a red giant, likely incinerating Earth before Andromeda arrives. Even if Earth somehow survived, the actual merger would pose little direct threat to any star system. individual stars would simply be shuffled into new galactic orbits. The night sky would look radically different, brilliant with new stars, warped by tidal distortions, but the space between stars would remain as vast and empty as ever. The Milky Way, in fact, has already absorbed numerous smaller galaxies throughout its history. The Sagittarius dwarf elliptical galaxy is currently being torn apart by the Milky Way's gravity, its stars streaming in long loops around our galaxy. The Canis Major dwarf galaxy may also be in the process of disruption, though its very existence as a distinct galaxy remains debated among astronomers. The ghostly stellar streams discovered by surveys like Gaia reveal the remnants of ancient dwarf galaxies long since cannibalized, their stars now woven into the Milky Way's halo. This is how large galaxies grow, by devouring smaller ones. The hierarchical assembly of structure in the universe begins with tiny fluctuations in the primordial matter distribution, which grow under gravity to form the first small galaxies. These small galaxies merge to form larger ones. The large galaxies continue to grow by accumulating satellite galaxies and occasionally merging with other large galaxies. It is a process of cosmic accretion played out across billions of years. When two large galaxies merge, the event can have consequences beyond the galaxies themselves. The gas funneled toward the center of the merger remnant may feed the central black hole, transforming it into an active galactic nucleus that blazes with radiation visible across billions of light years. In extreme cases, the feeding frenzy can trigger a quasar, one of the most luminous objects in the universe, powered by matter spiraling into a supermassive black hole at rates that would consume entire stars every year. Galactic collisions also demonstrate something profound about the nature of cosmic violence. It is not always destructive. Just as supernovae create the heavy elements necessary for life, galactic mergers trigger waves of star formation that populate the universe with new suns and new planets. The compression of gas clouds, the gravitational stirring of stellar orbits, the eventual assembly of larger galactic structures, all of these processes contribute to the ongoing evolution of the cosmos. Without mergers, galaxies would remain small, relatively static, and perhaps less capable of hosting the complex conditions necessary for life to emerge. The Andromeda Galaxy continues its approach, crossing roughly 110 kilometers closer every second. In human terms, that seems fast, about 400,000 kilometers per hour. But the 2.5 million light-year gap that separates our galaxies is so vast that this approach rate produces no perceptible change within a human lifetime, or even within all of recorded human history. The collision, if it occurs, remains billions of years in the future. For now, Andromeda hangs in our autumn sky as it has for all of human existence, a faint smudge of light, deceptively peaceful, revealing nothing of the trillion stars it contains or the cataclysmic encounter that may eventually unfold. It is a reminder that cosmic catastrophes operate on timescales that dwarf not just human lives but entire geological epochs. The universe is patient in its violence, willing to wait billions of years to bring two galaxies together and reshape them into something new. At this very moment, as you listen to these words, particles from the depths of space are passing through your body. Most are protons, the nuclei of hydrogen atoms, though some are heavier atomic nuclei: helium, carbon, iron, even uranium. They arrive from all directions, traveling at nearly the speed of light, having journeyed across the galaxy for millions of years before reaching Earth. We call them cosmic rays, and they represent one of the universe's most mysterious and extreme phenomena. Cosmic rays were discovered by accident. In the early 20th century, scientists noticed that electroscopes, devices used to detect electric charge, gradually discharged even when shielded from known sources of radiation. The presumption was that radioactive materials in the ground were responsible. But in 1912, the Austrian physicist Victor Hess took an electroscope aboard a balloon and descended to 5,000 meters. To everyone's astonishment, the rate of discharge increased with altitude. The radiation was coming not from below, but from above, from space. Hess received the Nobel Prize in Physics for this discovery in 1936. The term cosmic rays is somewhat misleading. These are not rays at all, but particles, primarily protons, about 90%, with the remainder consisting of helium nuclei, about 9%, and heavier elements, about 1%. They span an extraordinary range of energies, from modest particles produced in solar flares to ultra-high energy monstrosities that carry more kinetic energy than a professionally pitched baseball. The lower energy cosmic rays originate from our own sun. During solar flares and coronal mass ejections, protons and heavier ions are accelerated to energies of millions to billions of electron volts. These solar energetic particles can reach Earth within hours of a solar eruption, posing radiation hazards to astronauts and occasionally disrupting satellite electronics. The March 1989 geomagnetic storm we discussed earlier was accompanied by elevated cosmic ray fluxes that contributed to satellite anomalies. But the truly extraordinary cosmic rays come from far beyond our solar system. Intermediate energy cosmic rays, with energies ranging from billions to trillions of electron volts, are thought to originate from supernova remnants within our galaxy. The shock waves from stellar explosions, expanding into the interstellar medium at thousands of kilometers per second, act as natural particle accelerators. Protons and atomic nuclei bounce back and forth across these shock fronts, gaining energy with each crossing in a process called diffusive shock acceleration. Over thousands of years, particles can be boosted to energies vastly exceeding anything achievable in human-built accelerators. The evidence connecting supernova remnants to cosmic ray acceleration has grown steadily stronger. Observations of gamma rays from remnants like the Crab Nebula and the remnant of the Hunter 6 supernova reveal the signatures of extremely high-energy particles colliding with surrounding gas and radiation. The Fermi Gamma Ray Space Telescope has mapped these gamma ray emissions in detail, confirming that supernova remnants are indeed cosmic particle factories. But here is where the story becomes truly strange. At the highest energies, above 10 to the 18 electron volts, or 1 exelectron volt, cosmic rays enter a realm that pushes the boundaries of known physics. These ultra-high energy cosmic rays, or UH-Heckers, are extraordinarily rare. Only about 1 particle per square kilometer per century arrives with energy exceeding 10 to the 20 electron volts. Detecting them requires enormous ground-based arrays that monitor vast areas of atmosphere for the cascades of secondary particles produced when a cosmic ray strikes an air molecule. The most famous ultra-high energy cosmic ray struck Earth on October 15, 1991. Detected by the Fly's Eye Observatory in the Utah desert, this single particle carried an estimated energy of 3.2 xe10 to the 20 electron volts. To put this in perspective, this is approximately 50 joules of energy, about the same as a baseball traveling at 100 kilometers per hour, concentrated in a single subatomic particle. It was moving so close to the speed of light that in a year-long race with a photon, it would have lost by mere thousandths of a hair. Physicists, stunned by the observation, dubbed it the "Oh my God" particle. The "Oh my God" particle's energy was 40 million times greater than the highest energies achieved in the Large Hadron Collider, the most powerful particle accelerator ever built by humans. No known astrophysical process can easily explain how a single particle could be accelerated to such extremes. The standard mechanisms, supernova shock fronts, active galactic nuclei, gamma ray bursts, all have theoretical limits that struggle to reach these energies. Adding to the mystery is the so-called GZK cutoff, named for physicists Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin. In 1966, they predicted that cosmic rays with energies exceeding about 5x10 to the 19 electron volts should not be able to travel far through the universe. At such energies, protons interact with the cosmic microwave background radiation, the afterglow of the Big Bang, and lose energy rapidly. The expected cutoff implies that the most energetic cosmic rays must originate relatively nearby, within about 160 million light-years. Yet when researchers traced back the trajectory of the "Oh my God" particle, they found no obvious source, no nearby active galaxy, no recent supernova. nothing that could plausibly have produced it. The mystery deepened in 2021 when the telescope array in Utah detected another ultra-high-energy cosmic ray of comparable magnitude. Named Amaterasu after the Japanese sun goddess, this particle carried approximately 2.4 x 10 to the 20 electron volts, the second most energetic particle ever detected. When researchers traced its arrival direction, they found it pointed toward an apparent void in the large-scale structure of the universe, a region with few galaxies and no known energetic sources. As one astrophysicist colorfully put it, the particle seemed to come from absolutely in the middle of nowhere. How can particles with the energy of bowling balls arrive from cosmic voids? Several possibilities exist, none entirely satisfying. The particles might be deflected by intergalactic magnetic fields, causing their apparent arrival directions to point away from their true sources. They might originate from sources we simply haven't identified yet, perhaps dormant, supermassive black holes that occasionally reactivate. Some theorists have speculated about exotic origins, decaying super-heavy dark matter particles, topological defects in spacetime, or physics beyond the standard model. The composition of ultra-high energy cosmic rays adds another layer of complexity. Most cosmic rays are protons, but at the highest energies, observations suggest an increasing fraction of heavier nuclei, helium, carbon, perhaps even iron. Heavy nuclei can be accelerated more easily to extreme energies than protons, but they are also more easily deflected by magnetic fields, making source identification even more difficult. A 2025 study of neutrinos produced by proton-photon collisions suggested that among the very highest energy cosmic rays, fewer than about 70% are protons, the remainder likely being heavy ions. Cosmic rays are not merely astronomical curiosities, they have practical consequences here on Earth. The continuous rain of particles striking our atmosphere produces showers of secondary particles, pions, muons, electrons that reach the surface and even penetrate underground. These secondary particles contribute to the natural background radiation that all life on Earth has evolved with. They also cause bit flips in computer memory and can interfere with the operation of aircraft electronics, particularly at high altitudes where atmospheric shielding is reduced. For astronauts, cosmic rays pose a more serious concern. Outside Earth's protective magnetic field and atmosphere, astronauts are exposed to cosmic ray fluxes orders of magnitude higher than on the surface. During the Apollo missions, astronauts reported seeing flashes of light when they closed their eyes, the result of cosmic rays passing through their eyeballs and triggering their optic nerves. For future missions to Mars, which would take many months outside Earth's magnetosphere, cosmic ray exposure represents one of the most significant health risks, potentially increasing cancer rates and causing neurological damage. Earth's magnetic field deflects many lower-energy cosmic rays, particularly near the equator, where field lines run nearly parallel to the surface. This geomagnetic shielding creates the Van Allen radiation belts, regions where trapped particles accumulate. During geomagnetic storms, when the magnetic field is disturbed, more cosmic rays can penetrate to lower altitudes, contributing to the radiation doses experienced by airline passengers and crew. The polar regions, where magnetic field lines plunge into the atmosphere, receive the highest cosmic ray fluxes, which is why aurora, produced when solar particles follow field lines into the atmosphere, appear at high latitudes. The study of cosmic rays connects to some of the deepest questions in physics. These particles have been accelerated by the most powerful natural processes in the universe. Understanding their origins requires understanding the extreme environments of supernova remnants, active galactic nuclei, and perhaps exotic phenomena we have yet to discover. The highest energy cosmic rays probe physics at energies far beyond what any human-built accelerator can achieve. And every second, these cosmic messengers pass through your body, through the walls around you, through the planet beneath your feet. They have traveled millions of years, accelerated by cataclysms beyond imagination, carrying encoded within them clues to the universe's most violent processes. We have intercepted only a handful of the most energetic ones. We understand their origins only partially. The universe, it seems, still has secrets to reveal. and it delivers those secrets one particle at a time from the depths of space. We tend to think of planets as orderly objects, dutifully circling their parent stars, bound by gravity into stable configurations that persist for billions of years. Our own solar system reinforces this impression. 8 planets tracing predictable elliptical paths, a system that has remained largely stable since its formation 4.6 billion years ago. But this picture of cosmic order is, in many ways, an illusion. The universe is filled with worlds that have no sun, planets that wander alone through the eternal darkness of interstellar space, orphaned from any stellar parent. These are the rogue planets, and they may outnumber the stars themselves. The existence of rogue planets was predicted long before any were discovered. Computer simulations of planetary system formation consistently showed chaotic early histories. Young planetary systems are violent places, with multiple protoplanets jostling for orbital territory, gravitationally scattering each other into new trajectories. In many simulations, some planets gain enough energy from these gravitational encounters to escape their birth systems entirely, flung outward into the void at velocities exceeding their star's escape speed. Other planets might be stripped away by close encounters with passing stars or ejected when binary star companions disrupt their orbits. The models predicted that for every planet remaining in a stable orbit, perhaps several others had been lost to interstellar space. The first observational evidence for free-floating planetary mass objects came in the early 2000s, when astronomers identified very low-mass objects in young star-forming regions like the Orion Nebula and the Sigma Orionis cluster. These objects were too small to sustain hydrogen fusion, too small to be stars, yet they existed independently, not orbiting any visible companion. Whether they had been ejected from planetary systems or had formed in isolation like miniature, failed stars remained unclear. The discovery demonstrated that planetary mass objects could indeed exist without stellar hosts. The technique most useful for finding rogue planets is gravitational microlensing. When a massive object passes in front of a more distant star, its gravity bends the starlight, temporarily magnifying the background star's brightness. The duration and shape of this magnification event reveal the mass of the intervening object. Unlike other detection methods, microlensing can find objects that emit little or no light of their own, making it ideal for detecting cold, dark, wandering planets. Microlensing surveys have revealed that rogue planets are astonishingly common. A landmark 2011 study using data from the microlensing observations in astrophysics collaboration suggested there might be nearly 2 Jupiter-mass rogue planets for every main sequence star in the galaxy. Subsequent analyses have refined these estimates, with some studies suggesting the ratio could be even higher for smaller Earth-mass worlds. Current estimates propose there may be trillions of rogue planets in the Milky Way alone, potentially outnumbering the stars by ratios of 7 to 1, or even 20 to 1 in some calculations. In January 2025, astronomers achieved a breakthrough, the first confirmed measurement of both the mass and distance of a rogue planet. The object, detected during a microlensing event designated KMT 2024 BLG 7992, was observed simultaneously from ground-based telescopes and the Gaia Space Telescope. This dual perspective allowed researchers to measure the microlensing parallax, tiny differences in how the event appeared from different vantage points, which enabled a direct calculation of the planet's mass. The result: approximately 70 Earth masses, or about 22% of Jupiter's mass, placing it in the Saturn mass range. The planet lies roughly 10,000 light-years from Earth, drifting through the galaxy with no star to call its own. The mass of this particular rogue suggests it likely formed within a planetary system and was subsequently ejected. Objects that form in isolation, condensing directly from collapsing gas clouds like miniature stars, tend to be more massive. The Saturn mass rogue fits the profile of a world that once orbited a star, perhaps for millions of years, before gravitational chaos sent it spiraling outward into permanent exile. How does a planet get ejected from its home system? Several mechanisms can accomplish this feat. The most common involves gravitational interactions between planets during the early chaotic phase of system formation. When two planets pass too close to each other, they exchange orbital energy. One planet may be kicked into a more elliptical orbit, while the other gains energy and spirals outward. If the energy gain is sufficient, the planet achieves escape velocity and departs the system forever. Simulations suggest this process is particularly effective in systems with multiple giant planets, where strong gravitational perturbations are common. Binary star systems are especially efficient at producing rogue planets. The gravitational dynamics of two stars orbiting each other can destabilize planetary orbits over time. Even very wide binary companions, stars separated by thousands of astronomical units, can eventually perturb their planets into chaotic trajectories when passing stars nudge the binary orbit into a more eccentric configuration. The result? Planets that survived for billions of years are suddenly ejected when the stellar dance becomes too violent. Our own solar system may have contributed to the population of cosmic wanderers. Computer models of the early solar system suggest that a Neptune-mass planet, sometimes called Planet 9 in popular discussions, though this hypothetical object differs from the proposed distant planet of the same name, may have been ejected during the gravitational reshuffling that sent Uranus and Neptune to their current orbits. Smaller bodies were certainly scattered outward. The Oort cloud, a vast shell of icy objects surrounding our solar system at distances up to 100,000 astronomical units, likely contains trillions of cometary bodies that were flung outward during planetary migration. Some of these objects undoubtedly escaped entirely, becoming interstellar travelers. In October 2017, astronomers discovered the first confirmed interstellar object to pass through our solar system. Named Oumuamua, Hawaiian for scout or messenger from afar, this elongated, reddish object was spotted by the Pan-STARRS telescope as it swung past the Sun on a trajectory that was clearly unbound, meaning it had arrived from interstellar space and would never return. Oumuamua was small, perhaps 100 to 400 meters long, and its tumbling cigar-like shape sparked endless speculation about its origins. Whatever Oumuamua was, asteroid, comet fragment, or something stranger, its detection implied that interstellar space is teeming with such objects. Statistical analyses suggested that at any given moment, several interstellar visitors might be passing through our solar system undetected. For rogue planets, the prospect of encountering our solar system is far more remote. The odds of a Jupiter-mass rogue planet passing within the orbit of Neptune have been estimated at roughly 1 in a trillion over the next 1,000 years. Such an encounter would be catastrophic, potentially destabilizing planetary orbits throughout the inner solar system. But the probability is so vanishingly small as to be essentially zero on any timescale relevant to human civilization. What would existence be like on a rogue planet? At first glance, the answer seems obvious. Cold, dark, lifeless. Without a star to provide warmth, surface temperatures would plunge toward absolute zero. Any atmosphere would freeze solid, coating the surface in layers of nitrogen or carbon dioxide ice. Yet surprisingly, some scientists have speculated that certain rogue planets might harbor conditions suitable for life. The key is internal heat. Radioactive decay of elements like uranium, thorium, and potassium generates heat within planetary interiors, heat that persists for billions of years regardless of stellar proximity. On Earth, this radioactive decay contributes significantly to our planet's internal heat budget. A sufficiently large rogue planet, particularly one with a thick hydrogen atmosphere to trap escaping heat, might maintain liquid water beneath an icy surface. Such subsurface oceans, warmed from below by geothermal energy, could potentially host microbial life, sustained not by sunlight, but by chemical energy from hydrothermal vents. This concept of a Steppenwolf planet, named for the lone wolf of Hermann Hesse's novel, remains highly speculative. We have no evidence that any rogue planet possesses such conditions. But the possibility illustrates how life might persist in environments far removed from our star-centric assumptions about habitability. If rogue planets with subsurface oceans exist, they could serve as cosmic lifeboats, carrying microbes across interstellar distances over millions of years. Panspermia, the hypothesis that life spreads between worlds via natural mechanisms, might find its most effective agents in these wandering worlds. Rogue planets also challenge our understanding of what a planet even is. The International Astronomical Union's definition of a planet requires the object to orbit a star, which would exclude free-floating worlds by definition. Yet a rogue planet that was ejected from a solar system is, in every physical sense, the same object it was before ejection. Same mass, same composition, same internal structure. The distinction seems arbitrary. Some astronomers have proposed that objects below about 13 Jupiter masses, the threshold for deuterium fusion, should be classified as planets regardless of whether they orbit a star, while others argue for classifications based on formation history rather than current location. The upcoming Nancy Grace Roman Space Telescope, scheduled for launch in 2027, will revolutionize our understanding of rogue planets. Its microlensing survey of the galactic bulge is expected to detect hundreds of free-floating planetary mass objects, including potentially 400 Earth-mass worlds, far exceeding the roughly 25 rogue planets detected to date. These detections will provide the statistical sample needed to understand how many rogue planets exist, how they are distributed by mass, and whether their population is consistent with ejection from planetary systems or requires additional formation channels. Stars, too, can become wanderers. Hypervelocity stars, objects traveling fast enough to escape the Milky Way entirely, have been discovered racing through our galaxy at speeds exceeding 1,000 kilometers per second. The most extreme examples appear to have been ejected by gravitational interactions with the supermassive black hole at the galactic center. When a binary star system ventures too close to Sagittarius AE, tidal forces can tear the pair apart, capturing one star while flinging the other outward at tremendous velocity. These stellar exiles will eventually leave the Milky Way behind, destined to wander the intergalactic void for eternity. The universe, it turns out, is full of wanderers, planets without suns, stars without galaxies, objects cast out from their birthplaces by the chaotic dynamics of gravitational interaction. They drift through the darkness between stars, invisible to all but the most sensitive instruments, carrying with them the histories of the violent events that sent them into exile. Some may harbor frozen oceans, some may carry the seeds of life. All remind us that cosmic order is provisional, that gravitational systems can eject their members as easily as they bind them, and that the darkness between the stars is not truly empty. Somewhere out there, perhaps closer than we imagine, a world the size of Earth drifts silently through the interstellar medium, its surface locked in eternal ice, its interior perhaps still warm with the memory of formation. It has no sun to rise, no seasons to mark the passage of time, no sky except the unchanging stars. It is alone, and it will remain alone, wandering the galaxy for billions of years until the stars themselves burn out. It is an orphan world, and the universe is full of them. We have traveled far together through the catalog of cosmic catastrophes, from the explosive deaths of individual stars to the slow collisions of galaxies, from the violence of our own sun to the silent wandering of orphan worlds. But now we must confront the ultimate catastrophe, the one from which there is no escape, no recovery, no next chapter. We must ask, how does the universe itself end? This is perhaps the most profound question humans can pose. Every other catastrophe we've discussed is local, temporary, survivable in principle. Stars explode, but new stars form from the debris. Galaxies collide, but they merge into larger structures. Even mass extinctions, devastating as they are, leave survivors who rebuild the tree of life. But the death of the universe is total. It is the end of all possibility, the final dimming of every light, the cessation of every process that could ever produce change, complexity, or meaning. And according to our best understanding of physics, it is inevitable. The story begins with a discovery made in 1998 that shocked the physics community to its core. Two independent teams of astronomers studying distant Type 1a supernovae to measure the expansion rate of the universe found something impossible. They expected to find that the expansion was slowing down, gradually decelerating as the mutual gravitational attraction of all the matter in the cosmos pulled everything back together. Instead, they found the opposite. The expansion is accelerating. Distant galaxies are receding from us faster and faster, propelled by some unknown force that acts in opposition to gravity. This force was named dark energy, and it constitutes approximately 68% of the total energy content of the observable universe. We do not know what dark energy is. We cannot detect it directly. We infer its existence solely from its gravitational effects, or rather, its anti-gravitational effects. Dark energy appears to be a property of space itself, a kind of cosmic repulsion that grows stronger as space expands, driving the universe toward an ever more rapid dispersal of matter and energy. The discovery of dark energy transformed our understanding of cosmic fate. Previously, cosmologists had debated whether the universe would expand forever or eventually collapse back in on itself, the so-called Big Crunch scenario. Dark energy rendered the Big Crunch essentially impossible. The universe will expand forever, and that expansion will accelerate without limit. The consequences of this eternal expansion are collectively known as the heat death of the universe. Heat death is not about temperature in the familiar sense. It refers instead to the thermodynamic concept of entropy, the measure of disorder, of energy dispersal, of the universe's inexorable march toward equilibrium. The second law of thermodynamics tells us that entropy always increases in closed systems. The universe is, as far as we know, the ultimate closed system. Over time, energy becomes more evenly distributed, temperature differences diminish, and the capacity to do useful work, to power stars, to drive chemistry, to sustain life, gradually disappears. Let us trace the timeline of heat death, beginning from the present and extending into a future so distant that the numbers themselves become almost meaningless. For the next several trillion years, the universe will continue much as it is now. Stars will be born, live, and die. Galaxies will merge, as we discussed when contemplating the Milky Way's potential collision with Andromeda. New planetary systems will form around newborn stars. Life, if it exists elsewhere, may flourish on countless worlds. This is the stelliferous era, the age of stars, and we are living in its early chapters. But the raw material for star formation is finite. Hydrogen gas, the fuel that powers stellar fusion, is gradually consumed and locked away in stellar remnants. Around 10 to the 14th years from now, 100 trillion years, the last stars will flicker out. The universe will enter what cosmologists call the degenerate era. No new stars will form. The only remaining stellar objects will be the cold remnants, white dwarfs slowly cooling toward absolute zero, neutron stars spinning down over eons, black holes lurking in the darkness. White dwarfs, the corpses of sun-like stars, will continue to radiate faintly for an almost incomprehensible time. A white dwarf cools asymptotically, approaching but never quite reaching absolute zero. After perhaps 10 to the 15th years, these remnants will have cooled to just a few degrees above absolute zero, emitting virtually no detectable radiation. They will become black dwarfs, hypothetical objects that have never been observed because the universe is not yet old enough for any white dwarf to have cooled to this state. During the degenerate era, an occasional burst of energy might still occur. Brown dwarfs, failed stars too small to sustain hydrogen fusion, might occasionally collide and briefly ignite. Neutron stars might merge in the rare event that two happen to spiral together. But these events will be vanishingly rare in a universe grown cold and sparse. Then comes a process that may or may not occur, depending on physics we do not yet fully understand. Proton decay. According to some grand unified theories of particle physics, protons are not truly stable. Given enough time, they will spontaneously decay into lighter particles, positrons and pions, which themselves decay into photons and neutrinos. The half-life of the proton, if it decays at all, is extraordinarily long. Current experimental limits place it at greater than 10 to the 34th years. But in the timescales we are now contemplating, this is practically instantaneous. If protons decay, then all ordinary matter will eventually dissolve. White dwarfs, neutron stars, planets, asteroids, everything made of atoms will gradually disintegrate into radiation and subatomic particles. The timeline for this process is roughly 10 to the 40th years. After that unimaginable span, only black holes will remain as coherent structures. But even black holes are not eternal. In 1974, Stephen Hawking demonstrated that black holes emit radiation, now called Hawking radiation, through a quantum mechanical process at their event horizons. This radiation carries away energy, causing the black hole to slowly shrink and eventually evaporate entirely. The process is extraordinarily slow. A stellar mass black hole would take about 10 to the 67th years to evaporate. A supermassive black hole containing 1 billion solar masses would persist for roughly 10 to the 100th years, a Google years. When the last black hole finally evaporates, the universe enters the dark era. Nothing remains but a diffuse sea of photons, neutrinos, and whatever exotic particles have survived the eons. These particles drift apart as space continues to expand, becoming ever more isolated from one another. The temperature of the universe asymptotically approaches absolute zero. Time itself becomes meaningless, as nothing changes, nothing happens, nothing remains capable of marking its passage. This is heat death, not a dramatic explosion, not a catastrophic collapse, but a slow, quiet fade into eternal, changeless darkness. It is the universe reaching thermodynamic equilibrium at its maximum possible entropy. It is the end of all possibility. But heat death assumes that dark energy behaves as a cosmological constant, that its density remains fixed as space expands. What if dark energy is something stranger? What if its density increases over time? This possibility gives rise to a far more violent end: the Big Rip. In 2003, physicist Robert Caldwell and his colleagues explored what would happen if dark energy's pressure exceeded its energy density in a particular way, a condition characterized by an equation of state parameter less than -1. Such phantom energy would not merely accelerate the expansion of the universe, it would cause that acceleration to increase without bound. The expansion rate, the Hubble parameter, would eventually diverge to infinity in finite time. The consequences are apocalyptic. As phantom energy strengthens, it will first overcome the gravitational binding of galaxy clusters, tearing them apart. Then, individual galaxies will be disrupted, their stars scattered. Solar systems will be unbound as the expansion between a star and its planets exceeds their gravitational attraction. Planets themselves will be torn apart. In the final moments, atoms will be ripped apart, electrons stripped from nuclei, nuclei torn into their constituent protons and neutrons, and finally, even those particles may be destroyed. Caldwell's original paper calculated a hypothetical timeline. For a particular set of parameters, the Big Rip would occur approximately 22 billion years from the present. In this scenario, the Milky Way would begin to be torn apart about 60 million years before the end. Our solar system would become unbound about 3 months before the rip. Earth would be destroyed about 30 minutes before the final singularity, and then, in the last fraction of a second, atoms themselves would be shredded. The Big Rip is not considered the most likely fate of the universe. Current observations suggest that dark energy's equation of state is very close to -1, consistent with a cosmological constant rather than phantom energy. But the measurements have uncertainties, and we cannot rule out a Big Rip scenario entirely. The true nature of dark energy remains one of the deepest mysteries in physics. A third possibility, largely discounted but worth mentioning, is the Big Crunch, the collapse of the universe back in on itself. If dark energy were to somehow reverse, or if the universe contained more matter than we believe, gravitational attraction could eventually halt the expansion and begin a contraction. Galaxies would approach each other, the cosmic microwave background would blue shift and heat up, and eventually, all matter would converge in a singularity reminiscent of the Big Bang's origin point. Some speculative scenarios suggest this could trigger a new Big Bang, a cyclic universe endlessly expanding and contracting. But dark energy's discovery has made the Big Crunch seem vanishingly unlikely. So where does this leave us? What meaning can we find in contemplating the end of everything? Perhaps this: the fact that the universe will end does not diminish the significance of what happens within it. The stars that shine today are no less beautiful for knowing they will eventually burn out. The life that has emerged on Earth is no less remarkable for knowing that Earth itself will someday be consumed by the dying sun. We exist in a brief window of cosmic time, the stelliferous era, when stars burn, planets orbit, and complexity can flourish. This window will close, but while it remains open, there is light, warmth, and the possibility of consciousness contemplating its own existence. We began this journey by looking up at the night sky and recognizing that the apparent peace of the cosmos conceals unimaginable violence. We traced that violence from the deaths of individual stars to the fates of galaxies, from threats in our own solar system to the ultimate destiny of the universe itself. And through it all, a pattern emerged. Destruction and creation are intertwined. Supernovae destroy stars but seed the cosmos with heavy elements. Galaxy collisions disrupt structure but trigger new waves of star formation. Even the death of the universe in some speculative models might give rise to new universes born from the quantum foam of spacetime. You are here, listening to these words, because cosmic catastrophes made your existence possible. The atoms in your body were forged in stellar explosions billions of years ago. The planet beneath your feet coalesced from the debris of ancient supernovae. Your very consciousness is the universe becoming aware of itself, contemplating its own violent history and uncertain future. That is not a small thing. In a cosmos of cold equations and indifferent physics, the emergence of beings who can understand those equations, who can feel wonder at the spectacle of it all, represents something precious, perhaps the most precious thing in existence. The universe will end. But it has not ended yet. The stars still shine, the galaxies still turn. And we are here, in this moment, alive and aware, witnesses to the cosmic drama unfolding around us. Thank you for joining me on this journey through the mysteries behind cosmic catastrophes. If you found this exploration meaningful, consider subscribing to Deep Calm Science and sharing this video with others who might appreciate the wonder of our violent, beautiful universe. Hit the notification bell so you'll know when we embark on our next cosmic adventure together. Until then, keep looking up. The universe has more mysteries to reveal, and we have only just begun to understand them.